Okay, hello everyone. We'll get started in just a moment. So if you're getting ready to sit down, please go ahead. Okay, so hello everyone. We're really happy to see so many people show up for the tutorial. We're really excited about this topic and hope we can get you excited about it as well. We have a tutorial on synthetic data in the era of LLMs today with 5 great presenters, 4 of whom could be here in person. So first is Vijay from CMU, Vijay Viswanathan, and Alisa Liu from University of Washington, Yizhong Wang from University of Washington, and Xiang Yue from Carnegie Mellon University can't make it today, but he will be here virtually. And I'm Graham Neubig from Carnegie Mellon University. So they'll have their turn, but I get to go first. So first, I'd like to talk a little bit about motivation for generating synthetic data. And there's a lot of reasons why we might want to do this. And the first is that data is kind of equated with NLP process nowadays. Architectures are more and more homogenizing to similar shapes, and the determining factor between a system that works and a system that doesn't is more and more lying in the data. There's a number of ways that we can build data, and synthetic data has been used in all of them. The first is through pre-training or straight-up language modeling on raw text. The second is for supervised fine-tuning, where you have an input X and an output Y, and you want to optimize the probability of the output Y. And finally, more and more recently, there's been a lot of work on reasoning, latent reasoning models that also have some sort of reasoning chain Z. And synthetic data is very useful in all of these cases. So where do we get data? Traditionally, we have gotten data in a number of ways. The first is scraping the internet. This is still very important, no matter what you do. It especially important for pre-training. Also labeling manually, which we've done a lot traditionally. We still do a lot of, but synthetic data is increasingly playing a role here. Also collecting data from system users. So if you're running a system, you can collect data that they consent to having collected. And creative curation. So you might not have data in exactly the form that you want, but you can take some sort of existing data and curate it into the shape that you like. So why is this not enough? The first is scraping the internet is too noisy. So we have lots of data that we wouldn't necessarily want to be using because it's not the best training data. It's also too massive. So we're very compute constrained nowadays when we train models. And so just training a large model on the entire internet is not enough. The second is labeling manually. Obviously, this is very expensive. It's becoming more and more expensive as we're tackling harder and harder tasks that require larger levels of expertise in order to solve them properly. And in many cases, annotators are not even available. So if we want to do highly sophisticated medical question answering in Vietnamese, we might not be able to find annotators who can do this easily. Collecting from system users. First, we have a chicken and egg problem. So in order to collect from system users, you need to have a system. In order to have a system, you need to have data. And you don't have data. So that's a problem. Another thing is privacy implications, obviously. So you can only collect data that system users consent to. And creative curation is great when you can make it work, but there's limited applicability, especially if you're constrained to doing particular deterministic varieties of curation. So synthetic data to the rescue. That's what we're going to talk about today. We want to create data order-made that is relatively clean, appropriately sized, not too big, and also not too small, and tailored to individual tasks that we care about. Also flexible in some ways. So, maybe not requiring a huge amount of manual engineering in order to make it work. But the problem is getting all of these at once is hard. So it's still, at this point in 2025, more of an art than a science, although we're making much better science, which we want to talk about today. And so, it still requires a lot of finesse. So some of the things that can go wrong with creating synthetic data. So the first thing that can go wrong is that I talked about X, which is kind of your inputs into your system. And these can be off. This is a major problem. So the first thing is you could create synthetic data that doesn't look very much like your true data. And the reasons for this are that, language models, if you're using them to generate synthetic data, really like generating particular types of data. They like generating well-formed text that may not look like the text that a social media user is creating, or they might create stuff that's topically different from the topics that users of a particular system like to talk about. Another thing is, even if they generate good data, it might be just a small subset of the data that you actually want, so for similar reasons. Another thing is the labels may be wrong. So, usually we want to generate synthetic data for tasks that language models are not good at already, because if they were good at it already, we wouldn't need to train, better language models to be good at it. And so inherently, we want to create data for tasks where language models fail. And if they fail at the task, they also fail at generating data for the task in many cases. And another thing is the reasoning may be flawed. So even if they can generate good data, or you're generating reasoning traces for, things where you already have labels, they might come up with reasoning that doesn't match, the true set of reasoning that you would like to have. So that's the problem statement. And now we want to cover, a lot of the methodology that goes into this. And so this is the overall outline for the tutorial. We're going to want to talk about how we evaluate data quality for about 15 to 20 minutes, how we create high quality synthetic data, how do we use synthetic data after we've created it, which we'll split into two parts, before and after the break. In particular, how do we do scenario-specific applications? So for example, for math or code or multilingual or multimodal tasks. And then finally, talk about some limitations, open questions, and future research directions in the area. So let me jump into the first part. So before we talk about how we create synthetic data, we want to get on the same kind of footing with respect to what we think high quality data is. And in order to do this, we need to think about how we evaluate synthetic data. So the most common way of evaluating synthetic data is through extrinsic evaluation. And what extrinsic evaluation means is basically we measure not the characteristics of the data itself, but how useful it is for downstream tasks. And so essentially what we do is we take method one, we generate a whole bunch of data from it, we train a model, and then we evaluate that model on whatever task we care about. And then we do the same thing for method two, and then we compare the two. So this is, what we really want in the end. Typically we're generating synthetic data for the purpose of training. But the problem is twofold. The first is that this can be very costly because you need to go in and train models every time you do it, and you need to run evaluations on them. The second reason is this is very indirect. So there's many conflated factors, like, for example, your model training might not go as well. And in the end, you're going all the way end to end to this model, and it's very hard to debug like individual instances of the data not working well. So to solve this problem, we also have intrinsic evaluation, and this is measuring specific characteristics of the data or the generation process. So the first and most obvious way we can do this is through measuring data correctness. And this is tricky, obviously, because we need to be able to measure whether the actual outputs are correct or not. And so what we do is we usually ask questions regarding the data using either automatic or manual methods. And I'm going to give just one example of these, of each of these techniques here in this section, but in the future sections, we're going to be talking about a lot of methods, and a lot of these methods use a lot of these evaluations. So you can also read the other papers in our bibliography. We also have the bibliography on the slides and the tutorial website. So this is an example from the self-instruct paper by Yizhong and others. And basically here, this specifically asked for manual annotations where they had quality review questions like, does the instruction describe a valid task? Is the input appropriate for the instructions? So this is, instruction input matching. And then is the output a correct and acceptable response to the instruction and input? And you can see that these kind of roughly align with the questions that I was talking about here. You know, is the instruction valid? So this would be kind of corresponding to the first one. And then is the data, is the input well corresponding to the instruction is maybe kind of a mix of the first and second, and the output being correct is the second. So you can see that you can directly associate these with the kind of desiderata of the data we want to be creating. The second is data diversity and coverage. And this is, again, really important because the data we might generate might not be very representative of the data that we actually want to be covering. And so the question here we want to ask is, how well does the generated data cover a plausible data distribution? And just to give one example from a paper data tune by people in our group is here we looked at gold standard data. We looked at, and then we looked at two methods for generating synthetic data. So the first is just straight up generating synthetic data. The second is generating transformed data from existing data. And we'll talk more about this later. But what we did is we measured the unique bigrams per example. And the unique bigrams per example basically tells you how much diversity is there in the data from the point of view of word bigrams. And we could see that there's a lot more diversity in the transformed data, demonstrating that we're avoiding the pitfall of generating very homogeneous synthetic data. There's a lot of other metrics that are used as well. There are other dimensions like privacy and fairness and distributional similarity. And there's even toolkits that are designed for evaluating synthetic data. So this is a very recent paper called Synth Text Eval. And basically, it attempts to survey a lot of the different evaluation metrics that are used for evaluating synthetic data. And it's also a very good survey of the evaluation metrics that are used in synthetic data. So if you want to dig more into this topic specifically of evaluation metrics, I can definitely recommend this paper as a good reference for you to take a look at. So another thing that I'd like to highlight is we use language models for synthetic data generation. And a question might come up, which is, okay, which language model should we use for the purpose of synthetic data generation? And there's a number of trade-offs that we have here. So the first is, how good is it at generating synthetic data? The second is, how much does it cost, for instance? So if we want to generate a really large synthetic data set, using Claude Opus or O3 or something like this, a model that is very, very expensive to generate from might give you very high quality data, but it might not be the best choice from a cost perspective. And so we recently created a benchmark called Agora Bench, which we're actually presenting here at the ACL conference, which measures synthetic data by different LMs based on its ability to match manually created data for extrinsic measures and at what cost. And the evaluation metric we designed for this is we assume that gold standard data is kind of, manually created data is kind of a gold standard. And we measure the difference between training a base language model on synthetic data and the base language model trained on manually created instruction tuning data. And we compare a bunch of language models, both from the point of view of the final accuracy gained, final accuracy recovered, and the cost of generating the data. So that's a first start. And next, we will be turning it over to Alisa. But in the meantime, if there are any questions about the kind of overall stuff, I'd be happy to take them. Like to come on. Yes. The link of the website, is it on the, cool. Yeah, I'll put it up and we'll keep it up there for like 2 minutes. Sorry, I don't know how to jump to the beginning with this clicker, so you'll have to wait for a second. Okay, there it is. Synth data ACL at github.io. You can leave it up there for a anything else while we wait? Or? So the question generally was, how will we generate data for like out of domain scenarios? And I think we're going to talk about that a bit. So we can follow that later. Okay. I think we've had the link up for long enough.
Is it possible to go to slide 18 directly? Or did you put it?
Right.
Oh. Okay, it's fine. I'll do it. Okay, hi everyone. I'm Alisa. I'm a PhD student at the University of Washington. And in this next section, I'll be talking about approaches for creating and filtering synthetic data. So we'll be going through the following approaches to data creation, starting with sampling-based data generation. And actually, before we get into sampling-based data generation, I want to cover some history first. The term knowledge distillation came from Hinton et al.'s seminal paper in 2015. As motivation in this paper, they discuss how large models have a lot of ability to learn structure and data, but they aren't suitable for deployment because of their size. And in contrast, small models are worse learners. They're less capable. They have less expressive capacity for learning the, data, but they're more suitable for deployment because of their smaller size. So the idea of distillation is to first train a big model, which we call the teacher, and then distill that into a small model that is trained to mimic the teacher's predicted probability distribution over the labeled classes. So here in this illustration, you can see the yellow boxes. Those correspond to like 7 possible outputs. The teacher's making a prediction that's a probability distribution over the 7 possible classes, and the student is trained directly to mimic that entire probability distribution. And so crucially, this differs from the traditional method of training over ground truth data, because instead of matching a one-hot encoding of the next word prediction, you're instead matching the entire probability distribution that's being produced by the teacher. And of course, you can also interpolate the distillation objective, this new objective, with the traditional objective just by adding an additional hyperparameter that allows you to simultaneously optimize for both. A year later, Yoon Kim and Sasha Rush bring knowledge distillation to NLP, and they take it one step further from word level distillation to sequence level distillation. Thanks. The authors observed that instead of training the student to mimic the teacher's predicted probability distribution over the vocabulary, which is a very local prediction, in theory, we could instead train the student to mimic the probability that the teacher would assign over the set of all possible sequences, so over the set of possible text. Of course, doing this naively is intractable, right? Because there are infinitely many possible sequences of words. But one way we could approximate this is by producing high probability sequences from the teacher via something like beam search. Then you could train the student directly on those with a traditional supervised training objective. So this is probably starting to sound a lot like the type of data generation and distillation that we know and love now. And the authors here find that impressively, the student can match the performance of the teacher while running 10 times faster. So these two definitions of distillation that we covered, one where the student is trained to mimic the probability distribution over the vocabulary, and one where the student is trained directly on outputs generated by the teacher, are both still used today. Both of these forms of distillation are still in use today. But the latter is what we mean by sampling-based data generation in this tutorial. So just again, sampling-based data generation, you generate data from a language model, and then you train another language model. And they could be the same language model. Thanks, Yizhong. Okay, so in this sequence level distillation paper, you may have noticed that the generated data was under the same task that the teacher was trained to perform. So the teacher in that example was trained for machine translation. So you can use it to generate translation data and then train a student on it that would also then do translation. This began to change when generalist language models became more capable. And crucially, when GPT-3 introduced this idea of in-context learning, where the model can perform arbitrary new tasks as long as you can describe that task in natural language via in-context examples. So this enabled a new application of using language models for data generation. As long as you can provide examples of the task that you're interested in, the language model will naturally continue with examples of the same task. So one of the first papers that I can think of to use general language models to produce task-specific data came in 2021 from Timo Schick, where they focused specifically on the sentence similarity task. So if you remember, this task is essentially given a pair of sentences to classify them as either similar or dissimilar. And they show that you can create new examples of this task by simply prompting the model to write similar or dissimilar pairs of examples. Is this working? Okay. Then in about 2022 or so, we began moving from task-specific models to general instruction following models. So now the type of data that you care about is not something like data for a classification task like sentence similarity, but instead generic instruction following data. So instructions paired with responses that answer those instructions. And for this type of setup, the key idea behind sampling-based data generation can be applied again. Instead of prompting models to generate more examples under a given task, we can generate completely new tasks. So that's the prompt on the left. You can just ask a language model to come up with a series of tasks and give it some examples of the types of tasks that you might be looking for. And then it'll generate a new task. Like in this example, it's given an address and city to produce the zip code. And then now that you have that task, you can ask the model to produce example input and outputs under that task. So examples under that task, and it will do that for you. The two seminal papers to demonstrate this idea were self-instruct and unnatural instructions, which actually came out, I think, within a day or so of each other. And so in self-instruct, from just starting from just 175 seed examples, you can use this pipeline to then produce arbitrarily many new examples. In the original paper, we went up to about 100,000 new examples. In terms of results, we found that fine-tuning GPT-3 on self-generated data actually led to better performance than fine-tuning on any of the existing instruction data sets at the time, even though they were created through much more labor-intensive processes. And it even approached the performance of InstructGPT, which was the best proprietary instruct model at the time. The unnatural instructions authors also did diversity analysis of the generated data. And they found that the generated data that they had produced from just a small set of seed examples was actually more diverse than human written data. So what this plot is showing is the average pairwise similarity. So you just sample pairs of examples from the data set and calculate their similarity with BERT score. And lower here means that it's less similar. So it's more diverse. And they found that unnatural instructions, which is the generated data, is more diverse than supernatural instructions, which was human written. Both papers then did qualitative analysis of the examples. So Graham talked a little bit about this before. The results here were really surprising. Both papers found something remarkably consistent with each other, which is that only half of the generated examples were actually fully correct. So this means that we just saw the models perform, like models trained on this data performed really well, but somehow this is despite the fact that the data is actually only about half correct, half fully correct. At this point, I want to cover some takeaways from these early efforts on synthetic data generation. A lot of these might seem obvious in retrospect, but they really weren't at the time. So the first is that synthetic data can reflect creativity and diversity that's difficult to elicit from crowd workers. Crowd workers are not intrinsically motivated to produce creative and diverse output. Instead, if you're paying them to write examples with a particular instruction, they'll naturally find the easiest way to do that as fast as possible. And this often means developing easy heuristics or patterns and then collapsing into those and then producing very repetitive data. So by simply using language models and diversifying your prompts and sampling a lot and being clever with the entire pipeline, you can create data that is very different than the kind we were able to achieve before with crowd working. We also saw that diversity can be more valuable than correctness. Initially, it seemed like a negative result when we found that in self-instruct, a lot of the generated data was not actually as correct or high quality as we may have wanted it to be. But it actually hides a really interesting takeaway, right? Which is that data correctness is potentially not as important as we thought before. And it's really about the diversity of the data, which adds a lot of value to model training. And this, I think, is a good, led us to start thinking about what counts as good data. We saw that synthetic data can also enable self-improvement. I didn't dwell on this before, but one unique aspect of this self-instruct pipeline is that the data generator and the model being trained are actually the same model. And this contrasts with the traditional distillation setup where you have a large teacher and a small student. But even in the self-instruct setup, if you strategically elicit the distribution of data that you want to train on, and then you train that same model on it, you can enable the model to self-improve. We're also starting to see data creation becoming a more complex pipeline. So hidden in every synthetic data generation paper are many, many details about how this pipeline was constructed in order to get the best data possible. These details are often not very intellectually interesting, but each is critical to actually having a successful pipeline that produces good data. Okay, so the theme among the next few approaches is that we'll add more controls to the data generation pipeline to further improve the quality and diversity. I'll be touching on the key ideas for each of these relatively briefly without going much into the results of the papers, but you'll see these topics covered again later with more concrete details. So the next approach we'll talk about is back translation. Back translation similarly originated in machine translation. The idea here is given an output to generate a corresponding input. So for something like translation, your output will be a sentence in the target language, and what you're doing is generating a corresponding translation in the source language. So we can look at English and Zulu as an example for this diagram. So suppose your end goal is to have a model that does Zulu to English translation. One way you might approach this problem by doing back translation is to first use the limited amount of naturally occurring data that you have to train an English to Zulu model. So that's the opposite direction of what you actually want. And then you'll use you have a lot of English data, so you can use that to produce then low quality Zulu translations. We're assuming the model isn't very good because you don't have a lot of data for this language pair. But then the result is that you can train on your noisy Zulu data paired with English data to get to produce a model in the direction that you do want, which is Zulu to English. And this actually kind of makes sense, right? Because you're training the model to produce outputs in the target language, and you have a lot of data in the target, but you don't necessarily have ground truth data in the source. What you can do is produce noisy inputs, which is fine because the model is just conditioning on the inputs. It's conditioning on sentences in the source language, what it really wants to do is produce sentences in the target language, and you want the model to see a lot of diverse types of target outputs. Okay, in the modern NLP landscape, this idea gave rise to instruction back translation. So the idea here is really the same. We have lots and lots of web text, and we would like an instruction tuned model to be able to generate this large diversity of possible outputs. And to make this possible, what we can do is, given a web text, we treat that as the target output, and then we ask a language model to generate an instruction, a corresponding instruction that the output would be a good response to. I hope that makes sense. So in this example, the target output is this passage about the benefits of meditation. So this is sourced from somewhere on the web. And you're asking a language model, what kind of instruction could this be the answer to? And it generates, write an essay about the benefits of meditation. So then the idea is that you would take this generated instruction to write an essay about the benefits of meditation, and this output, which is like naturally occurring, and you could train an instruction model on it that now does the instruction following task, which is to condition on instructions and generate responses. Okay, so now I'll talk about a transformation of existing data. Here, the idea is that we will use or retrieve existing data, then transform it into an example under the desired task. This is very similar to back translation, but now we're making it a bit broader. And so in back translation, we always fix the output, right? We said this is the output, it's fixed, and we want to generate an input corresponding to the output. But more generally, you could imagine giving the model the flexibility to reshape both the input and the output. So transformation also allows us to take advantage of existing data in their available forms to then produce data in the desired form. Suppose, for instance, that there's a task that you care about, but you don't have any data under the task. What you could do is retrieve relevant data sets, automatically retrieve relevant data sets or documents, and then transform what you retrieve into data under the desired task. So in this illustration, the task that you want to create data for is given a piece of Python code to produce an English language description. And you can see that one very relevant data set that might be useful for this is a task that's kind of in the opposite direction, which is given a code problem to write a code snippet that does what the problem is asking for. So you can transform this pretty easily, as you can imagine, into the desired task. Of course, this is all automatic, right? So the retrieval is being done automatically, and the transformation is also being done automatically. But you're turning a data set that's kind of like natural language to code into a data set from code to natural language, a natural language description. As another example, you could ground your generations in a given knowledge graph. So the dialogue dataset SOTA was created this way. What they did was they used a very large social common sense graph. I think they used Comet. And what they did was they first sample a tuple from this knowledge graph, and then they transformed that tuple into a narrative, and then they transformed that narrative into a dialogue. So here the example, the tuple is if a person X needs to move closer to the goal, then they would need to take the first step. And then from there, you transform that into a story about Madeline and her coach and how Madeline needs to take a step. And then from there, you transform that into a dialogue between Madeline and her coach. And they find that this works way better in terms of creating both natural and diverse outputs compared to just prompting the language model, over and over again to create dialogues, because then inevitably it will collapse into a few kind of repetitive cases. Of course, the largest source of data that we probably have is the web. And in a paper called Mammoth 2, the authors scrape web pages, then they train a classifier to identify whether a web page is likely to contain questions and answers within the web page. So they use this then to identify candidates. And then they extract question-answer pairs from this raw, messy web text, and then rewrite the extracted question-answer pairs into something that is more substantive and like valuable for training instruction tuning. So in this example, I think the retrieved web text is looks like it's from, I don't know, Stack Exchange or maybe something like that, or Math Stack Exchange. You extract a question answer pair from it, and then you rewrite it. The answer now has like step-by-step reasoning, so it's valuable for instruction tuning. And you can even like follow this idea of transforming existing data for pre-training. So in this paper titled Rephrasing the Web, the authors create synthetic data by asking language models to rephrase web data in different output styles. So for instance, you could give the model a piece of web text and then ask it to paraphrase it in the style of Wikipedia. And the authors surprisingly found that when controlling for the number of training tokens, training on synthetic rephrases of web text is actually even better than training on the original web text. And they hypothesize that this is because the rephrased data may be cleaner. So whereas web data might be messy and contain like formatting idiosyncrasies, if you rephrase it into clean output that perhaps has the style of high quality data like Wikipedia, then that can be really helpful for model training. So I guess to recap a little bit, this section was about transforming existing data. So you're taking data that's readily available and then transforming it into data of the format that you want under the task that you care about. Another way of adding control to synthetic data creation is by bringing back a little bit of human effort through human AI collaboration. So why would this make sense? We've seen that language models are creative and diverse, but they're not reliably correct, right? So you'll recall that in self-instruct, about half of the generated examples were found to be fully correct. This can be improved by grounding generations in existing data, but in the end, models aren't flawless, and they're still prone to things like hallucinations. In contrast, humans are pretty good at verifying correctness, and improving the quality of an example. But we're not good at enumerating examples of what we know how to do. So the hope behind human AI collaboration is to leverage the strengths of each party for data creation. So backing up in time a little bit, one early exploration of this idea was for creating data for the natural language inference task. So in our work, Wan Li, we first used GPT-3 to generate new NLI examples by identifying clusters of examples that demonstrate challenging reasoning patterns. Then we prompt GPT-3 to create new examples that demonstrate the same pattern. And finally, what we do is we ask crowd workers to revise these generated examples and also assign it with a gold label. So at the time, asking humans to do the NLI task was much more reliable than asking a model like GPT-3. So what this does is it turns a writing task for crowd workers. So traditionally NLI, you ask people to write examples of NLI from scratch into instead an editing task. And this is desirable because, again, enumerating examples of the types of inferences we know how to do is really, really hard. There's lots of diverse inferences that we know how to do, but we might not think of them if we're just asked to sit down and write examples. But in contrast, editing a given example is easy to do, and it also has a huge impact on the quality of the data. If you don't want a human annotator to touch every example, you can also train a router to selectively determine when an example should receive human attention versus when a generated annotation would suffice. So this idea has been used for labeling preference data, where the authors essentially train a router to determine whether a human annotation, like whether a model would be capable of answering it with high confidence, or otherwise it should use a human annotator instead. As the final approach to synthetic data creation, we'll talk about symbolic generation, which doesn't require language models at all. So in a recent paper, some researchers explored the idea of doing an initial phase of training before pre-training, which they call pre-training, and you'll do this pre-training phase on formal languages. The type of formal languages data that they explore training on includes like languages, which essentially involves balanced parentheses. as well as this other kind of text, which repeats the same string over and over again. So that's the bottom row in this table. And they find that pre-training on Dyke languages is actually even better than pre-training on a matched amount of natural language from a data set like C4. And they hypothesize that this is because the formal languages text, even though it's not even natural language, captures the same type of hierarchical dependency structures that are found in natural language. And as a result, pre-training on this leads to a good model initialization for training on natural languages. Okay, so to summarize the approaches section, we talked about sampling-based generation, where we generate examples from scratch from language models. And then we talked about back translation, where you're given an output and asked to generate an input, or the model is asked to generate an input. Transformation of existing data, which is a broad class of methods. I keep going backwards. A broad class of methods where you transform existing data into examples of the desired task. Human AI collaboration, where you mix language model generation and human annotation. And finally, symbolic generation, which is rule-based and does not use language models at all. This was a brief overview of approaches for synthetic data creation. And in the following sections, Vijay and Xiang will discuss more concrete examples of how these approaches are used in modern language modeling development pipelines. But before I hand it over to them, I also want to briefly cover some approaches for data filtering. So essentially, every pipeline for synthetic data generation will also have some kind of filtering stage to remove low quality or repetitive examples. Roughly, the kinds of filtering can fall into diversity filtering, quality filtering, and correctness filtering. So one method of diversity filtering is by using surface level heuristics. For instance, you can remove generated examples that are very similar to existing examples in your data set by using something like Rouge-L, which just measures lexical overlap between two pieces of text. So this is really simple. You generate an example, you check whether the overlap between the most similar example in your data set exceeds a certain threshold. And if it passes that threshold, you're like, it's too similar, so you don't use it, you filter it out. You could do something similar to this, but instead of using lexical-based similarity metrics, you could use embedding similarity. So for instance, what the QDIT method does is it embeds generated examples with the language model being trained, and then it performs clustering to essentially find clusters of examples that would be represented similarly under the language model. And then you select the highest quality examples from each cluster, right? So this is a bit more sophisticated. You're saying, okay, there's types of reasoning that are being exemplified in the data set. I only need so many examples of each type of reasoning. And in particular, I'll choose the best examples I have within each cluster. You could also tag the examples with semantic attributes. So in this paper, what they do is given like an instruction example like this, you can tag it as, okay, this is an information request. This is about technology. It's about healthcare. And then within each tag, maybe there's only a certain amount of data that you actually want to keep. So you can ensure that you have like a diverse representation of tags, but you don't want to have too much data within each tag. Recent work also showed that you could measure data diversity in terms of an example's extrinsic impact on model performance. So in particular, you could represent an example by the loss gradient that it would induce under a proxy model. And then you could basically measure the diversity of the resulting data set as the entropy of these gradients. The intuition here is that if two examples like induce different loss gradients under the proxy model, then that means that they will teach the model different things. And what you really want is a data set that is diverse in terms of what it would teach the model. And they find that this definition of data diversity, unlike measures based on semantic or lexical similarity, actually correlates with the robustness of the resulting model. So on the right figure here, on the x-axis, you have the data diversity score measured in terms of like loss gradients. And then on the y-axis, you have the robustness of the model as measured by the out-of-domain accuracy. So evaluated on data that's not like what it was trained on. And you can see that they're correlated essentially. So the more diverse your data is, the more robust your model is going to be. But it's only true if you use the right measure of data diversity. For quality filtering, one popular modern approach is to use reward models. So for instance, if you want to generate an SFT dataset given a pool of prompts, you can sample K responses for each prompt and then just take the best of K. Keep the one that achieves the highest reward under your reward model. And then you can do SFT over this best of K data. A paper titled Raft introduced this idea, and they found that you can do this over multiple iterations. So you're generating data, finding best of K for each prompt, fine-tuning the model on that data, and then you can generate new data with the updated model and repeat this process over and over again. And what this plot here is showing in terms of the results is that as the number of iterations increases, so as you do more iterations of generation and fine-tuning, the average reward of examples produced by that model continues to increase. And these days, this is a really popular baseline to compare to. It's considered like a way of doing reinforcement learning without actually doing reinforcement learning. And so if you are doing RL, you should compare it to something like this as a baseline. Finally, you might demand something that is a little less nebulous than high quality, and instead seek out data that is verifiably correct. And this idea is really useful when you're generating reasoning traces for instructions with known ground truth answers. So suppose you have math problems and you know the true answer to the math problem, like maybe it's 5 or something, but you don't have a reasoning trace that takes you from that question to the final answer. So this type of like verifiably correct filtering was used in a method called STAR. So what they do is given examples like this where you have the instruction and final answer, you generate reasoning traces and you only keep the ones that actually lead to the correct final answer. You can go a little further. So for generations that do not lead to the correct final answer, you could give the model a hint in the form of the true answer. So you tell the model, oh, the answer is 5, like try again, to generate a reasoning trace that would lead you to the correct final answer. And then the model is generally able to do that, so it'll generate a new reasoning trace, and you can train the model exclusively on reasoning traces that actually lead to the correct answer. Recently, this kind of correctness-based filtering was also used for the construction of DeepSeek R1. So in their case, their SFT data started from math problems with ground truth answers, as well as coding problems with unit tests. And then they used their most recent model checkpoint to generate reasoning outputs. And then they only keep the ones that actually lead to the correct answer. Then they do SFT on this data. And then afterwards, they do more reinforcement learning. But it shows that this idea of using verifiably correct, like passages with verifiably correct outputs is really powerful. Okay, so I think that's all I have for this section. I covered different approaches to generating synthetic data as well as approaches for filtering synthetic data. Open to questions if y'all have any. Yes, in the gray shirt.
So is it okay to analyze which shows the higher diversity? Because you said that the 50% of the generated data shows the incorrect example. So what about the distribution on the here to the correct the answers to the human written maximum?
I'm not sure if I fully understand the question. Is it to do verify the answers from output by self-instruct or?
More diverse than the human generator because the only 50% of data is correct. So,
Oh, I see. You're saying that the incorrectness of the data is contributing to the diversity. Okay, I would say that having looked at the data, this probably does not account for much of the diversity. Like, you have to remember that the data that this is coming from is like traditional NLP tasks. So stuff like sentiment classification, analysis, stuff that we've seen again and again, maybe formatted in different ways. But the resulting data is often stuff that's like not like what we saw, like not like traditional NLP tasks. It's possible that some of the diversity is coming from like the correctness of the output, but I don't think that's usually what diversity metrics measure, right? It's about the semantics of the question and answer. Yeah, thanks for the question though.
I remember you said that diversity is more important than correctness. Can you elaborate a bit on that?
Well, okay, I didn't say it in quite those words. I wasn't like diversity is always better than correctness. But I was saying that one takeaway from the early synthetic creation of instruction tuning data showed that even though the even though the answers are not often correct, training on that was still better than training on existing data sets that probably had higher correctness. So that just means that like correctness is not all there is to the data, and just having diverse data can be very valuable for training. Does that help? Okay.
Hi, nice tutorial so far. I was curious to learn how good we are at understanding the performance of generation and filtering across model sizes. Presumably, larger model needs significantly more careful curation.
I'm not, okay, so the question is about whether larger models need more careful curation.
I think that's almost a given. I guess the question is how well do we understand all the techniques that you presented and which ones generalize across model scales and which ones don't?
That's a good question. I'm not sure I have a good answer to that, in that I haven't seen work on how model size should impact the type of filtering, like the stringentness of the filtering that's done. I suspect that what you're hypothesizing is true, though. Sorry, I don't have, do the other organizers have answers to this question?
Yeah, definitely. Like if your model is stronger, you need like higher quality data to like basically elicit the model's capabilities, and like without hurting. Actually, bad data might hurt the model's performance. So I think in terms of the empirical relationship,
Work to be done, I guess.
I think there are some like analysis on like the relationship between SFT data quality versus the model performance, but not like for all the stages right now. Yeah.
Yeah. Okay. Thank you.
One other small thing I can say about this is in the context of in-context learning, there's been demonstrations where actually stronger models benefit more from having correct labels, and weaker models can learn from incorrect labels because they learned the formatting, which they were getting wrong in the first place. Whereas the stronger models actually learn the formatting, and then they also learn to do the tasking correctly. So I do think that higher quality is necessary there, but I haven't seen it from the point of view of synthetic data.
Sounds like a good scaling laws paper.
Thanks for the great presentation. I want to know a bit more of your insight in comparison of the like traditional distillation over the distribution of the target model versus data generation, basically. So you said a bit of a history, but I'm not sure if you're going towards the conclusion that the traditional distillation is basically outdated, or is it like orthogonal to synthetic data generation?
That's a great question. So the question was about the two definitions of distillation and like whether they're like which one's more helpful now or used more in modern development. So I think a lot of this information tends to be proprietary. Like my understanding is that large model development labs are often doing something like distillation. So you'll train the biggest model that you can, you'll make a compute optimal, and then you'll distill it into a much smaller model that is capable of running on one GPU or something like that. In terms of whether like what kind of distillation they're doing, I've actually heard both, and there's like pros and cons to each one. So for instance, if you're doing the form of distillation where you're matching the entire probability distribution, it's often the case that there's a ton of noise, right? Like the vocabulary is really large, and there's a lot of like very low probability logits that you don't actually care a lot if like the model predicts like 10 to the -13 or -15 or something like that. But under KL divergence, a difference like that actually matters a lot. So it's possible that you don't want to do like distillation at that level, but I think people are still doing it, and it can work really well. I just don't know exactly how. That's my my understanding from the outside.
Am I audible? Yeah. So I wanted your input regarding reasoning traces and intermediate reasoning steps if you're creating a data set for that. So let's take an example of arithmetic reasoning problem. Suppose there is a word problem. We know that the final answer is 5. Okay. And if we are prompting the model to generate the intermediate reasoning steps to come to it, and you mentioned that suppose if the answer is wrong, or maybe the intermediate step is wrong, then we just prompt it again. Maybe like this is the final answer, try to come up to the right step. How would you go about validating the correctness of these intermediate steps? Because very easily, if I'm repeatedly prompting the model to just come to the right answer, it could very easily hallucinate too.
Yeah, for sure. It could be like, oh, the right answer is 5. I'll hallucinate some series of steps as long as the like last number in the passage is 5 or something.
Yeah, exactly.
That'll be fine. This is a really difficult problem, and as far as I know, it's actually really hard to do well. So there's stuff like process reward models, which score the intermediate steps of a reasoning trace. But the reason why, like at least the DeepSeek R1 paper talks about this a little bit. They say that they tried process reward models, and it was just really hard to get right. So one way you could get around this is by not giving the hints, like you just generate a lot, maybe you get a bit more clever with the sampling, but you only want to keep the generations that lead to the right answer without ever using the hinting approach where you tell the model what the right answer should be.
Okay. Okay.
yeah.
So maybe some level of human intervention would be required, which is just checking if the intermediate steps are correct or not.
Yeah, you
At
could
least some-
definitely do human AI collaboration, but if you have the budget, yeah.
Oh, okay. Cool.
And also the expertise. I think that can get pretty hard
Yeah,
for
yeah.
math problems that we work on today.
Okay. Thank you.
Hey, hi. So I had a question regarding the nature of distribution of the data that we get. Like, let's say, for example, any big model from which we try to get the data we need, we kind of get it based on the distribution on which it was trained. Like, let's say, for example, to simplify, we need more geographically diverse example for some use case. Like, let's say from geography region X, the model has been trained so much. So with whatever the instruction, however I try to control it, I'll always end up with more from X. But for my downstream task, I need more, like, let's say equally distributed from different regions. So can we do it with less human intervention, or even if no human intervention, if possible?
Let me make sure I understand the question. And someone asked to tell me if we're running out of time because I'm not keeping track. But the question was about, okay, let's say you prompt a model in a certain way, but the distribution you care about is actually different. Like the test distribution is different.
Yeah, yes.
I mean, yeah, I think this is a really broad problem unless I'm, missing some details. You could try to elicit the right type of data by like filtering maybe the outputs that you have. You're like, oh, this output is more similar to the type of distribution I'm looking for, and then feed those back as in context examples. So you're gradually shifting the distribution of generations closer to what you're looking for. But it depends on the exact setup of your problem. There might be better techniques.
Okay.
I hope that's helpful. Sorry. Yeah.
One other thing is you asked specifically about geographic regions, and we're gonna, Xiang is going to talk about that a little bit later.
Okay.
But also, if your distribution is biased, you can think about how to get an unbiased distribution. And we're going to talk about, some of the retrieval-based methods. There was also talk about the knowledge graph-based methods, and for geographic distributions, we've looked a little bit into knowledge graph-based methods for that. So I'd be happy to talk about that more. We don't have a publication yet, but happy to chat. Yeah.
Hi, thanks for the tutorial. My question is, how much is the quality of the resulting model that you train with the synthetic data upper bounded by the quality of your source model for generating this data? And maybe especially what is the impact of scale and quality of your generating model on the data and the resulting model?
Right. So I think it probably depends a bit on the generation process. So if you're doing this naively, probably it is upper bounded in some sense by the model that you're generating data from, but you could invoke tools. This is something I didn't talk about, but perhaps you equip the model with the ability to use tools to improve the correctness of its generations. You could involve human annotation effort for instance. So these are ways that you can kind of try to break that ceiling of the teacher model's performance. And again, you can, I guess, try to elicit the right type of data that you want. By skewing it in the direction of things that you want. You could use reward models to do filtering. So that way, even if the teacher models only write 1 out of 1,000 cases or something like that, if you have a good way of verifying correctness, then you can pick out that 1 out of 1,000 examples and then train on that. So these are all ways that you can get around it. But I guess there's a sense in which that's true. You're bounded by the quality of tools that you have.
Thanks.
Yeah.
I want to add one point to the previous question. There is some assumption on the weak to strong supervision of the models. Basically, the assumption is if your model is very strong and your synthetic data generated by a weaker model, actually teach the model only the format or the style to perform a task, and at test time, it actually generalizes using its own knowledge combined with the styles that are taught by like a weaker model. So in that sense, it might not be bounded by the weaker model. Yeah.
Right, so Alisa just introduced the core algorithmic building blocks for synthetic data generation. And now we'll be discussing how to use synthetic data. And there's really two levels of granularity in which we can explore how to use synthetic data. So firstly, let's understand that synthetic data is algorithms that support other algorithms. And so we can first discuss the high-level fundamental learning algorithms that are used for language modeling. And then we can go into scenario-specific applications, which actually become really important when you're actually trying to get something that people will actually like using. And because these are both substantial, we'll split these into two. And I will cover the fundamental language modeling algorithms that synthetic data can enable. So synthetic data generation, as I said before, supports other algorithms, and the LLM development pipeline today in a simplified setup looks like this with roughly 4 classes of algorithms. The first is pre-training on unlabeled text, which is useful for learning features for a variety of tasks. The second is supervised fine-tuning, where you're learning either style or content for particular tasks of interest. And then RL training helps for incentivizing particular kinds of targeted behaviors that you want to improve on and you can measure. And then lastly, evaluation and analysis are absolutely critical. And while I've put it here at the end, evaluation really happens at every step or even inside every step. And so this is a very simplified pipeline. In modern NLP, these steps are actually interleaved and permuted in very custom ways. And like today, there are even kinds of new stages that combine these two. For example, mid-training is SFT followed by more pre-training. Continued pre-training is pre-training after pre-training already for a specific task or domain of interest. Preference training is this type of reinforcement learning that looks more like SFT. So just to say, we're going to cover these 4 broad categories, but understand that they can be used in a variety of custom ways. And these are, again, just a slightly more granular form of building block, building on what Alisa had mentioned before. Okay, so first we'll talk about pre-training. So pre-training is self-supervised. You are taking unlabeled text from the internet and formatting it into a format that looks like supervised data for a language model. And therefore, annotation cost is cheap. So you might wonder, why do we even need synthetic data here? And there are a couple of reasons, but the first is that bigger models require more data. And today's models have already basically been trained on all of the legal accessible digital data on the internet, and maybe even beyond that. So if we want to keep being able to enable scaling, then we need to do something about this. So synthetic data could be a solution, but does this even make sense? Let's just unpack that for a second, because LLMs aren't magic, and they can't invent new linguistic phenomena or new tasks or new facts that we care about in the real world. And so we would argue that there is a way around this, which is to either use language models on existing data that just may not be in the format that pre-training would desire, or being able to generate linguistic patterns in a more procedural way without needing language models at all. So firstly, for pre-training, one idea would be to use back translation, where, as we said before, back translation lets you convert data that might have one particular property into like a input-output pair. And in the FI paper from Microsoft, they generated code pre-training data that you might even call like mid-training today that obtains task-relevant code from the internet and then converts it into natural language code pairs. And this approach helps significantly on top of just general scraped data. So they started with 6 billion tokens of data scraped from the internet, and then they added 1 billion tokens that were code snippets from like Stack Overflow and other places on the internet, rephrased to look like natural language. And even though this new data was 1/6 of the size, it improves few-shot accuracy on human eval by almost double. And so to understand why this is, we can revisit a paper that Alisa mentioned that shows that scraped data that is reworded and cleaned up can just lead to faster training and also, or faster learning and better generalization. So you're not really adding new knowledge here, you're just producing it into a format that might be more consumable by an algorithm. And so if we're not needing to produce new knowledge for our pre-training, what if we instead completely removed any knowledge from that training data? How far could we go with that? And again, as Alisa showed before, pre-training on formal languages where we are simply exploiting the fact that languages have some kind of regular statistics and dependency structure can also enable learning. So this is all just to show that enabling pre-training can often have more to do with formatting and statistics than anything else. So continued pre-training is a particular form of pre-training that is for emphasizing data for a particular domain or task of interest. And this can be super helpful, but all it really is you continue the same pre-training objective, but on a different corpus than what your original pre-training was on. And this is really useful when you have data in your domain of interest. For example, biomedical questions from on cancer. That might be a domain, and you collect data on that domain and you train on that. But let's say you actually want to spin something up really quickly and you may not have data or resources available. You might want to look to synthetic data in this situation. So in this paper, Synthetic Continued Pre-Training, they consider a scenario where you have a model that's been pre-trained already, and now you have a small corpus that you want to continue pre-training on. This corpus is useful enough that you can get some kind of signal, but it's not really large enough to converge on a stable representation in that domain. And so in this situation, the algorithm they describe here is to extract a knowledge graph from this small corpus, use that knowledge graph to sample new combinations of entities or relations that were not actually in the original corpus, and then generate text that contains these new combinations of entities and relations. And this is an example of transforming existing data. The way I think about this is that LLMs are really good at hallucinating. We know this. So this is encouraging LLMs to hallucinate given conditioning on entities and relations that of interest, and letting them do what they do really well, which is hallucinating. And in this manner, you're able to outperform continued pre-training on that small corpus, which is the green line here. And you're also able to, this approach also enables faster learning than more naive forms of paraphrasing, because here you're sampling sentences to cover entities in a more targeted way. And the last point about pre-training that I want to mention is that This is really risky in some ways because pre-training is the keystone of modern language modeling. And if you overdo pre-training on synthetic data, you will alter the distribution of your data and therefore of your language model in really significant ways. Because real language has a long tail, it has a lot of low probability tokens that are meaningful, and synthetic data has significantly less of this. And so this is something to be mindful of when doing any kind of pre-training with synthetic data. So now let's move on to SFT, supervised fine-tuning. And first, let's ask, why do we do SFT? And here the answer is pretty clear. It might be to control the style of your model output. If you're writing legal text versus writing tweets, it might look different. It might be to specialize behavior for a particular task of interest, or even to add new knowledge or new knowledge that your original pre-training data might not have had. So as we mentioned before, distillation is the classic way to do SFT if you have a bigger model available. But there are some trade-offs here. Distillation can be cheaper than manual annotation in terms of paying a person to do work. On the other hand, there may be a situation where your student is bounded by the performance of the teacher, although this is a little bit more complicated as some of the questions mentioned before. And increasingly, proprietary language models are being used, and these often have no distillation clauses. And in recent years, we've seen companies and practitioners get in a lot of trouble for deploying models that were actually distilling somebody else's model. So what do we do about this? How do we overcome the limitations of naive distillation? And we can make an observation, which is that a lot, not all, but a lot of the benefit of distillation simply comes from adapting the teacher's style. And so this doesn't really require training the model on any new information. So let's consider an extreme case here where we deliberately try to avoid giving the model any new knowledge and still find that it can help on tasks of interest. So here we're given a few-shot prompt, so a task description and 2 examples in that task. And in this setup, we ask the model to generate its own fine-tuning data for that task. So in this example, the task is NLI, and we generate an NLI data set and then fine-tune that same model on its own data. So here you're effectively using synthetic data as part of an instruction following algorithm without incorporating any external knowledge into the algorithm. This again is an example of sampling-based generation with the caveat that the teacher and student are the same. And we found that in our work that on both classification and generation tasks from natural instructions, this algorithm for instruction following was outperformed few-shot prompting or few-shot fine-tuning like TFew. And this difference was especially stark for generation tasks, which actually makes sense and is consistent with our understanding that what this is really doing is it's helping the model learn the format of the outputs that it should be generating. And so models are good at learning formatting even in a few-shot setting. And by generating more data there, you can improve the robustness of the model at generating examples that look right, even if it may not be learning how to actually make them right. And this is really similar to self-instruct, which we described earlier, where a model can teach itself to generate appropriate responses to instructions. And again here, there's no new information coming to the model, so we wouldn't expect new skills to emerge. But we can apply that same algorithm naturally with a bigger model, where it's the same algorithm as self-instruct, but you have a different teacher than the student. And the alpaca model, which was a really popular open source LLM from 2 years ago, applied this algorithm using GPT-3 as the data generator. And so interestingly, even though this model actually was incorporating external knowledge from a larger teacher. And in that paper, they used Llama 2 8B, I believe, or Llama 8B as the Llama 7B as the student and GPT-3 as the teacher. Despite acquiring new knowledge from a larger teacher, the student still mostly learned surface level behaviors like style or aversion to potentially risky content. And so in these plots here, which are the left is MMLU, which is like a multi-domain QA data set, and then benchmark, and then human eval is for code generation, and natural questions is like Wikipedia question answering. In all of these, we can see that this, even if we train on more and more imitation data sampled from the language model from GPT-3, the benchmark performance is not going up. And in natural questions, it's actually going down. So why is it that doing this recipe that seems very reasonable, where we distill from a bigger model, is not actually improving some of these really non-trivial skills that we care about from language models? The good news is that it is very likely possible to teach a smaller model or teach any model to do non-trivial skills via sampling-based generation. But a lot of the time, some pretty complex sampling strategies are necessary. So for example, in eval instruct, the intuition here is that they do very careful instruction design when doing this distillation process, where they start with the same data from alpaca, where we showed before it was not that effective at these QA or coding tasks. But then they randomly sample things like constraints on the instruction, like write a response with this in mind. And then they also were generating analogies to other domains to be able to have more coverage. And after doing this, they sampled responses from the teacher, which is like the classic distillation piece. And then they filtered out either instructions or responses that were of low quality. This might look like a response that starts by saying, sorry, I can't do that, or I'm not sure. Like those types of keywords, they just hard coded and removed those. So this was actually, this paper is very popular. It was very effective and overcame some of the issues that alpaca had shown. And then similarly, so in the previous example, we showed careful design of instructions can help overcome some of the issues with distillation. We can also carefully design the responses and training that we acquire from the teacher model. In Orca, they acquire a really, really large number of examples, 5 million examples. And then for most of these examples, there are reasoning traces, which are also trained on. So this is adding another piece of information that you might not even have during SFT in the beginning. They do some clever tricks with learning and data augmentation with system prompts. And using all these tricks together makes this pretty effective. The problem is that this is kind of a lot going on. It's a lot of work, and it could be a little fragile. So maybe are we just doing too much with these types of approaches? And in Mammoth 2, which was discussed earlier, there's the idea that just transforming a large amount of existing data might be even better. So just taking documents from the internet, extracting them into a question answering style format, and then refining it to add things like reasoning traces. That's definitely easier, and it might be even better. And it outperforms on the domains where we have data collection for. It outperforms Llama 3 8B instruct, which is trained on a very large amount of manually collected data. So the main takeaway here is, do you want to train on knowledge or subtasks with diverse coverage? If so, why not just extract them directly and use them, rather than trying to like coax them out of a proprietary language model in very unnatural ways? So now we've talked about pre-training and supervised fine-tuning. And so next up, we'll talk about RL training. But first, we're going to take a 30-minute break, get some coffee, do what you need to do, come back here by 4 o'clock, And until then, we have 10 minutes now for questions. If anyone wants, come to the mic or come up to me. Hi. Hi.
Thank you very much. So just a quick question. You presented to now kind of the approach. So if you would to data, if you rank which one we should go for, is it dependent on the domain, the task?
Which approach?
So the approach
Yeah, yeah.
present for constructing data.
It definitely depends on the domain, but I think my personal opinion, which is opinionated, is that the idea of retrieving data
From web,
from the web, for most things, this is, I think, the right idea. Like,
okay.
don't do everything from scratch. Use existing data to the extent possible and rephrase it or sample it. Yeah.
Okay,
So I think 90% of the time, this seems to work the best, but that's
even if
it
it's
depends.
medical domain.
maybe especially if it's something like medical domain, as I understand it, there's a lot of symbolic knowledge graphs and stuff used.
Yeah.
So why, like, I think using those is a great idea. And I think there's papers on using knowledge graphs, It's like what some of the ones I showed.
Okay, thank you very much.
I was wondering if you'd need more, maybe significantly more complex sampling strategies to capture something that is not trivially visible in the surface form. And then there are simpler approaches such as MAMP2
Yeah.
that actually does the same job. Then in principle and essentially, what is there that should be representative in the data that you're training your model over?
Yeah.
That would lead to, you know, capture of those, let's call them non-trivial, maybe dimensions of the data.
That's a really good question, and I don't know if there's a clear answer for what we are looking for in the data. One thing I'm pretty sure we want is coverage of, say, entities in the case of knowledge intensive tasks. So in Mammoth 2, like you're extracting, but by pulling from the internet, you can ensure coverage of entities or topics or domains of interest. And every like complex sampling strategy sort of is trying to do this in its own way. So you definitely want coverage of entities if you're doing some kind of knowledge-based processing.
So may I interfere and ask,
Yeah.
are you mostly doing it on, let's say, world knowledge tasks? Yeah. So
Yeah,
because I was not really sure what is the natural question task actually.
The natural question to ask.
Yeah.
In world knowledge.
No, just the task that you mentioned that actually.
The actors, movies, history,
Ah,
couple
okay.
of topics on Wikipedia.
Okay,
Yeah.
encyclopedic knowledge.
Knowledge intensive task. Yeah, so in here, like DPQA is like scientific knowledge question answering, and Big Bench Hard has other kinds of QA that might be medical QA
That
or.
is also like kind of benchmark specific. If you want to
Yeah.
improve your MMLU, go for STEM kind of things.
Is it possible if we go back to the slide that in which you mentioned that actually for the natural questions everything's plummeting?
Oh, yeah.
Oh yeah. So just to be sure here, the tasks that you're actually getting better over are, and I just want to have a.
None of these tasks, I'm showing all the negative examples.
All right.
None of these are getting better over.
Okay.
There are other kinds of, I think it was manual evaluation and like chatbot tasks like Alpaca Eval and Arena Hard. There, the model was getting better because the model was learning to adapt to the voice.
Dialogical maybe scenarios you mean.
Exactly. That kind of
Okay.
thing. Chatbot. Yeah.
And do you observe anything like any differences between an abstract reasoning maybe and I would call it again encyclopedia knowledge and abstract reasoning might be a bit different categorically.
Yeah, I think that even for things like, I mean, in Xiang's paper, they covered abstract reasoning, and even there, you might want to represent different reasoning styles. Like for math, it could be either, in the math example, different types of proofs or different domains of math, which will themselves have catered to different kinds of reasoning, right? And so you can still have coverage how you describe or quantify coverage is extremely domain dependent. And it's hard to like speak in generality about that. But I think that's what retrieval-based distillation can achieve or can make it easier than that sampling cannot.
Yeah.
Yeah.
Thanks.
Yeah, yeah. Let's go on from over there. Yeah.
So you have covered multilinguality here. Let's say you
That
are
will happen in the next section. Yeah.
okay, so now the current and one more question. So pre-training requires large amount of tokens, right? So
Yeah.
you are saying continuous pre-training, let's say creating new synthetic pre-training data.
Yeah.
So you cannot create that scale of synthetic data. You do continual pre-training, but that affect like in terms of let's say overfit, let's say forgetting or some kind of issue.
It will. And sometimes that's okay. Like if you're you're training a model for one task and you don't need to do other tasks, you actually
So
might
if it's
want
a
it
task
to.
specific or domain specific, it may not, but sometimes also requires where we should domain specific also require word knowledge. Right? So in that case, it might also help us.
That's a good point. That could be the case. If your task requires like synthesis of your new domain with existing knowledge, that could be a challenge. I agree. And I think that this I would be cautious about anything like this in that situation. But
So
if you're
any strategy create synthetic data for controlled pre-training.
yeah, so one thing that people have done is model averaging. Like you can do continued pre-training and then average it, do like model merging with your original model, and that sort of gets you, in a sense, the best of both. In the best case, it's the best of both worlds, where you're finding a global an optimum for your domain of interest, and then and then finding the previous state and finding the average there. So that could be an idea. Yeah, that'll be covered in the third section. Yeah. Thank you.
So I had a question with respect to this work you iterated several times on slide 71, I think. And it's one with diversity versus convergence.
Yeah.
Yeah. So, well, I haven't really read the work, so I'm not familiar with or perhaps there is a different work which covers it. But how do we know that this is just 300 billion of training tokens? That's not really that much. How do we know that these curves will not, join in the future, or since the graph is actually smaller data set? How do we know that at some point it will not saturate?
I think it absolutely would converge in the future, if I had to guess. Personally, 200 billion it's a decent amount of tokens. Like I think that Llama 380 was trained on a few trillion tokens, like maybe 4 trillion tokens. So this is 1/10 of that, which is still a lot. Like let's not like it's still like expensive. Like I know,
but very far from convergence.
Very
far from.
Yeah, you could go further. Yeah, I do think that if you have infinite compute, a lot of these decisions don't matter. You can ideally, if you just keep training on a huge amount of data, you'll kind of smooth out the issues with noise and data quality.
Perhaps my follow-up question is just whether you are familiar with some paper, or at least I can read it, but
Yeah.
that's the one which studied this phenomena of diversity versus convergence speed for a little bit longer than just initially.
I don't. Once Yizhong is back, you should ask him, because he worked on Olmo too, and they did. They did things with I know their paper. They published everything about their data. And so, oh, then you probably know what there is. Yeah, but I'm not sure exactly. It's a really good question though. Yeah. Thank you.
My question is about creating success data, and I hope to get your opinion. Because as you know, maybe many data success include some transforming or back translation and other. But I think many data synthesis methods needs query or source data. But how to create this query? But I think the query is most valuable. Because
Yeah. So, well, in natural in a self-instruct, they prompting.
It's just either prompting.
But just prompt, but then, and I think that like the more like a elegant way to do it is to prompt to have an instruction with some kind of seed topic, like say, like if you're doing math, generate a question that looks like these two in geometry, or yeah. So does that make sense? That's a pretty, I think that seems like a pretty mature way of doing instruction sampling nowadays.
Do you have does it have some method to create the knowledge or create the query which large language model doesn't know? For example, to explore new domains.
Well, if you create a query that the large language model doesn't know, how will you get the answer?
Yeah.
How will you get the answer? If the language model doesn't know it, then it's unanswerable, right?
So I think that is the big question because we need queries, then we can get the response. But if we don't have the query,
Well, you can do one thing you can do is also to solve this problem is instruction back translation, where you might start with the answer from the internet and then ask a query for which you already know what the answer is going to be. Like, yeah, does that make sense? Yeah.
Okay.
But the stuff you're asking is really open problems, and it depends a lot on the task. Yes.
This is just my response. I am generating role model, and the data synthesis is also my interest. But I think creating the most valuable query is mine.
Yeah, yeah, it's really important. Yeah, yeah.
Thank you.
Yeah.
First of all, regarding crazy.
I don't know if I don't know of anything that's done that. And this paper is relatively new as well. So yeah. Yeah, like is your concern that the paraphrasing would be worse in, say, Greek, or that the student model would be worse in Greek? Yeah. Yeah. I see. So I think that's probably true, but my feeling is that this task of rephrasing is pretty easy. Like it just requires understanding of shallow semantics and syntax. And I don't think you need like a super deep model with a ton of data to be able to do that. That's my vibe. I mean, yeah. Yeah. Right. Yeah. Yeah. So, and you have in a lot of languages, you have models of that size at least that are like converged, right? Yeah. So. Yeah. 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 Yes. Basically more epochs. That's right. With maybe the lower learning rate or something like that. Yeah. That? Oh, that's an awesome question. And I don't know yeah, so I mean, it is definitely the case that syntactic patterns vary from language to language. And so if you have like a language with 3-word order, it might be different than a language that's like with a very fixed word order. I don't know. You should really talk to Michael. I mean, he's here. You can find him on Huba. He's a cool guy. He's the first author of that paper, Michael Hu. He's at ACL, and I know he's trying to talk about this paper a lot. So yeah, he did another. Yeah. Hi. Okay. Yeah. Simulate that same direction. Yeah.
Some sample. Want to get more samples.
Yeah, absolutely. I mean, I think that's problem right now becomes samples from. That's right. That's right. Yeah.
But the now the goal is like when they have new data. That's already have some stuff.
Yeah. So I guess that would be more of data augmentation than synthetic data. Like these are very related ideas, but data augmentation assumes you have data to begin with. And so actually this is much easier when you have that situation. And one thing you can do is you can in Southwest exactly. That's where I'm going. Yeah, so here they sample instructions condition. They take 175 seed tasks and they sample instructions from those seed tasks. That same idea you could apply for some. You have a task that you want to do, say, text to SQL example, and then you might have a bunch of real text queries, and now you can sample from those text samples and say generate me. Here's the sample. Yeah, in context. Yeah, fewer instructions are more. Yeah, actually, okay, so there's a new paper that I actually wonder if that was here. It's called MACD. It's basically they sample instructions by prompting a model start code. Like they take llama the instruction and they just give it the start code and they generate text. And then the start code. And so then the model therefore will start by generating instruction from it that it's been fine-tuned. The idea there is large number of instructions. So by just letting it continue sampling, it has learned that you start with instruction and a response. And so the model will natively generate instruction something like that. So I think in this case, what you could do is you could first fine-tune your model small, which a lot of the case actually works. Like you can find if you have a model of AD, you can fine-tune it on 100 examples, and it'll probably learn something, and then you can now prompt it with nothing. That's like a slightly more clever. Bloom is also not a good model. Well, that's the consensus, yeah. Okay. So in this case, you have a model that has Nepali coverage. You want it to be better at Nepali instruction quality. So there's a couple of pieces here. One is the base. You are like the base model is probably the greatest permanent capacity. Second is the quality of your SFP data. And Alpaca is pretty good. Like I think nowadays there's better instruction quality data sets like ultra check one, probably more standard now. And I think it's probably better. And then third is how you price it. That would be better. Each of those are pieces you could over. It sounds like your base model, you don't have a lot of choice there because the poly is not the most important one. Okay, so let's say you can change. Now, my question would be, why is the exit failing? Is it that it's failing to train well or it's failing to generate? that would answer that. I guess perplexity going down versus thinking about equal amount of data. That would be one question. Not perplexity, or like, sorry, test training set loss. You did translate. Translate out back to you using a Google Translate or yeah, I think that's a really good idea, and I think that there's a way to make that right. It's supposed to be easy to talk language model. One other thing I think is interesting. So one problem with supervised fine tuning is what's called exposure bias. The idea that I'll talk about it, but the idea that you're training your model originally is not that good. It will make mistakes, but your training data is much better, and so it won't have those. And so imagine you're like starting a sentence, and then you sample one word that's completely wrong. Like, what is the capital of Austria? Say the capital of Germany is the answer. But that's bad, right? You should not have sampled Germany answer. And now the model in the training data never seen such a stupid mistake, and so it will not know how to recover. And so that's called exposure bias. And so there's a lot of techniques that have been about to address that. I would look into that. That could be like if you're basically the teacher model, if your student is really bad, then it will probably become even worse than that plan. Yes. Yeah. Yes.
And I hear that's that it's depending on I work or to be part of X.
They're both important, but it's diversity is very important.
If there is like pay all, like you find it because that
Yeah.
in my work last year, I only like verified like
You did? And
yes.
what did you find? I'm curious.
in a very like little like common generation task
Yeah.
that we found like we use the large language model to use different prompts.
Which models?
We use GPT for
Okay.
like to use different like prompts like to generate data and train the small language model. And we also find like diversity is like more important, like to improve both accuracy and diversity in smaller language models. So I'm very curious about it.
Yeah. Yeah. So I don't know exactly what the trade-off is. I think that's a really cool question. This paper of ours that Graham talked about, it answers this to some extent. It evaluates different language models, synthetic data generation, and interestingly, what they find is that what we found is that using so using the best teacher, which is Claude Sonnet, the best model is not always the best teacher. So like Claude Sonnet is the best on every task in this evaluation, but the data it generates is not as good for learning. And so I think the relationship between teacher accuracy and student, like what the student learns, pretty nuanced. I don't know if people totally understand that. Okay, thank you.
That's a good just play. Okay.
Okay, let's get started here. Please be seated so we can properly begin the second half of this tutorial. Okay, so in the previous sections, we've discussed how to evaluate synthetic data, fundamental algorithms for synthetic data generation, and we began talking about how to use these algorithms for supervising different language modeling tasks. And now we will continue our exploration of how to use synthetic data. So Previously, we discussed pre-training and supervised fine-tuning. Next, we'll go into reinforcement learning, which is becoming one of the most essential parts of the language modeling pipeline. And so first, let's think from a high level, why do we do RL? And so the goals of RL are, one is to learn from minimal supervision. It's often easier to rate a response than it is to generate that response. Another is that SFT only learns from what you should do, but what if you have examples of what you should not do? And then lastly, RL provides a token level signal rather than a, it provides a sentence level signal rather than a token level signal. And that can be really useful for reducing what's called exposure bias, where the student during decoding time makes mistakes that the teacher would have never made, and then it does not know how to recover from those mistakes. So when we talk about synthetic data for RL, we're talking about synthetic feedback. And this actually makes a lot of sense because it's often easier to verify a task than it is to generate a correct solution to that task. And to this point, synthetic feedback for RL is actually nothing new at all. In fact, it's pretty much standard in RL. For example, reward models are literally generators of synthetic feedback. And the way reward models are typically trained is you collect a bunch of prompts, you collect responses for those prompts, you have humans describe which one is better or make a list-wise ranking of those responses, and then you train a model to replicate those human preferences. And then you can use this model to grade sampled responses during RL. And traditionally, this training is done by assuming the Bradley-Terry model, where the Bradley-Terry model is a way to model continuous scores given only observations that are discrete preference pairs. So given response A and response B, you don't actually know what score response A or response B would have gotten. You just know that response A was better. And so this is the traditional way of doing synthetic feedback for RL. However, synthetic feedback for RL need not come from these Bradley-Terry reward models. It need not come from continuous rewards at all. For example, in LLM as a judge in that setup, you just have a model that you give a response to and you ask it to produce a grade. In this paper, Prometheus, they train a model through SFT that, given a rubric, a task description, and then a response, it produces a score for that response according to this rubric. And this method was designed for evaluation, but it can also be used for supervising RL. And interestingly enough, this model was itself trained on synthetic SFT data. So it's kind of synthetic data all the way down. And going even beyond this, you don't really need data for training at all when you're trying to have a producer of synthetic feedback. You can just prompt a model or sample a response from, say, 1 to 5 on a given criterion from a language model, and then that can be used directly for training with reinforcement learning. And even more simply, if you're doing something like preference optimization, like DPO, you don't even need to ask for a numerical score. You can just provide to a model 2 possible responses and say which one is better, and use that as direct supervision for DPO. And like Zephyr is a famous example of a paper that does this. And so people have this approach has actually become very popular, and it's also become quite complex, where there's some evidence that it's much easier to rate responses when you're given an explicit criterion. And so people now have like very large sets of criteria, like 16 criteria that cover helpfulness, harmfulness, different aspects thereof. And then you can like sample which of the two responses is better on each criteria, and then choose based on your mixture of what values you care about, which response is in aggregate the best one for your task. However, a problem here is that we've shown that it makes sense that you might want to explicitly consider specific aspects of response quality. But is it possible to actually a priori describe every aspect of response quality that you care about? And so a solution here, the answer is that it's clearly not. So a solution that we've described in a very recently posted paper is to generate checklists for each prompt, where through a slightly intricate mechanism, we extract a checklist for a prompt, and then we ask a separate judge model to score each response on each checklist item. And we do the scoring using a combination of a language model judge or verifier code, if that can be generated. And then we can use this to aggregate a single score for that response. And so on our evaluation, which was on instruction following, we found that this was pretty substantially more effective than most reward models on most tasks. And I think that this shows that using flexible criteria, maybe test time, training time criteria that are customized for each example is a really powerful idea. And so now I've discussed like 5 different ways of generating synthetic feedback. How do you even know which kind to use? And so for this, we have to discuss how to evaluate synthetic feedback. And there's a few ways that this can be done. The first is calculating agreement with human preferences. So the dataset reward bench is a really popular example of this, where it contains, for a small set of prompts, it contains response pairs and a human annotation of which response is better among those two in the pair. And then for a given reward model or judge, you hope that the model can agree with the human raters on which of these two responses was better. However, using something like reward bench it's a general purpose benchmark, and it does not capture the nuances of your particular task of interest. So if you want to evaluate a judge for a specific domain or task of interest, a popular approach is to use re-ranking as a proxy for how well that judge is aligned with your downstream metrics. The way you do this is pretty straightforward. For every question or prompt in that benchmark, you can sample a decently not large number of responses, like maybe 8 or 16. Use your judge to decide which of those is the best under its scoring function, and then use that re-ranked response in the benchmark's original evaluation metric. And if this makes the score go up, that suggests that your judge is actually well aligned with the things that you care about. And lastly, probably the most important way to evaluate judges if you're doing RL is through extrinsic metrics, meaning you actually train a policy using that judge as the supervisor. To do this, you have to choose an RL algorithm like DPO, like PPO, DPO, choose a base model and a set of prompts. You then do your RL procedure, which usually involves sampling responses for those prompts, grading those responses with the reward model, and then training the model to maximize those rewards. And then once you do this training procedure, you have a policy that you can then evaluate on the benchmarks of your choosing. The tricky thing is that these 3 ways of evaluating reward models or judges are often not correlated. And in particular, 1 and 2 seem to be mostly correlated, but 1, 2, and 3 are often not correlated. So let's give an example. And this really gets to an open question right now that I want everyone to think about, which is what makes a judge a good teacher for RL? And so one theory that seems very intuitive is that an accurate reward model is a good teacher. And that is probably true to an extent. But here we can, in this plot, the x-axis shows the reward model accuracy, the y-axis shows how long that reward model was trained for, and then the contour lines show how well a policy that's trained the convergence on that reward model actually performs downstream. And so what we see is that having a reward model that maximizes accuracy is actually worse for your policy performance than a reward model with sort of middle of the road accuracy. And this has been replicated separately by a bunch of different researchers. So I think this is like a pretty clear pattern that is not fully understood. One theory that's very compelling for this is that you actually need two ingredients for a good judge, not just accuracy, but also you need to have a reward distribution over all the responses for a prompt that has very high variance. So let's think about what this means visually. So on the left-hand side, and in this setup, this is a toy example where we have 5 objective categories of response quality: very bad, bad, neutral, good, and great. We want to make sure that the reward model, if it's accurate, always assigns a great response higher than good and a good response higher than bad. So a perfectly accurate reward model with low variance is the one on the left, where it will always rate a great response better than good. But the problem is that it rates all great responses. It does. If we think about the variance, which is the squared difference from the mean, the variance is actually very small here. To understand that, let's look at the middle plot here, where here the variance is actually maximum. If the mean is 0.5, and so the squared error from the mean could not be higher. And the accuracy is okay because we're rating good and great responses better than bad and very bad. But within those categories, it is making mistakes. And so an optimal accuracy and optimal variance reward model might look like the right-hand side, where you have sort of these discrete bands of response quality. And so there is currently an active effort to understand how much variance has to do with reward model quality in RLHF pipelines. But I don't think there's a clear answer. And so this is an open question. Okay, and then lastly, moving beyond RL, but staying within the world of feedback. Another kind of cheaper way of incorporating feedback is to just use feedback as a turn in a multi-turn conversation. You can, given a prompt, you can produce a response and then ask a separate model to grade a critique for that response. Use that critique back to the original prompt and ask back to the original model and ask it to refine that response. This is a self-refine. And this type of approach is nice because it doesn't require training. It's like an inference-only approach. And it can be really quite effective on many benchmarks. But the problem is that, as far as I know, it really only works when your model is already really good. And so this is another thing to consider and put in your toolbox of synthetic feedback. So lastly, we can talk about evaluation for a little bit. And the goals of evaluation are pretty obvious. They're to test model readiness and hopefully discover insights about either language in general or your task at hand. And so in prior work, we explored directly generating evaluation data using a language model as the data generator to sort of imitate a real data set that we might care about. So we had a held out data set, which was either like Squad or Konawa for Japanese to code generation. And then we generate synthetic evaluation data and we checked correlation between these two. We found that a lot of the time, the correlation was actually quite good, although it was not always the case. But interestingly, the synthetic evaluation data almost always overestimated the model performance by a lot, by like a factor of 2. So I think that the idea here is that if the input distribution that you have in your evaluation data is not really representative enough, then you might just cover the head of your distribution, and you won't consider all of the complexities or edge cases that a real task might produce. And in order to overcome this, how can we actually find more difficult examples for evaluation using synthetic data alone? So one way you can do this is if you have an accurate mistake classifier, you can deliberately try to elicit mistakes and use those. And this is called red teaming. And the basic idea is you generate a bunch of prompts, you compute which ones cause your model to make a mistake. That becomes a reward signal, and you use RL to try to incentivize generating prompts that produce a mistake. This could actually be done with a human as well. You don't need to use synthetic data to do this, but it helps you do it more cheaply. And it can help you have a more realistic evaluation using synthetic data alone. And so lastly, we also care about analyzing language models and learning insights about machine learning. And synthetic data has been used for this purpose since the advent of NLP. But as a modern example, Kasner et al. In 2020, they created a synthetic pre-training corpus using a set of facts and logical rules, like Jupiter is big implies Jupiter is small. And they then pre-trained BERT from scratch on this synthetic data, which has the nice property of you know exactly what went into this data and what properties it has. And using this approach, they learned that BERT was actually very good at learning single hop reasoning steps, but it struggled with two hop reasoning. So I think this is a really nice type of approach, and one that there's still a lot of space for these kinds of things for understanding models today. Okay, so far I've discussed fundamental language modeling algorithms. Next up, we will be discussing scenario-specific applications, and Xiang is on Zoom to talk about that. But before we get there, we have 5 minutes for questions.
Hi, thanks for the talks. My question is about the complexity of the data and curriculum learning. I've not heard about it in the way to use data. It's not specific to synthetic data. Do you have any thoughts about curriculum learning, the way to present the data based on the complexity to the models?
Yeah, so that's a curriculum. I think everyone can hear the questions, right? Curriculum learning actually makes a lot of sense potentially in data generation. And in the previous section on supervised fine-tuning, there was one paper that discussed this, which was about, it was Orca. In that paper, I'm pulling it up, but they used two different models as the teachers, GPT 3.5 and GPT 4. And GPT 4 is more expensive, so they had a much smaller amount of data that they fed to GPT 4. And they used a curriculum where they started out training on the output of GPT 3.5 and then finished with training on GPT 4's outputs. And so I think in this paper, they argued this is actually very effective, like an important part of their procedure. And so there is some precedence for this type of thing.
Yeah, because your example with the two hop and single hop is a bit in that direction. I mean, the is not small, is more complex than is
Yeah.
big. And
yeah, I think that's a really interesting idea. And I don't know papers that specifically do that. Oh, also for the questions, maybe all of the presenters can come up, and Alisa, if you wanted to come up as well to help answer anything.
I have one additional comment about that, which is like when you have synthetic data, you also typically have a small amount of real data, right? So the very natural thing to think is you want to train on synthetic data first and then train on the real data afterwards, because the synthetic data might be unnatural or noisy in some way. And that's true in some cases, but the opposite is true in other cases. And so just to give an example for like back translation for machine translation, you actually might not have a whole lot of human annotated data and it might be very biased towards a particular topic, or it might even be noisy because you can't get high quality translators. And so sometimes the synthetic data is actually of higher quality than the like real human data that you have. So I don't think there's any hard and fast rule about like what order you should train things on, but typically training on the highest quality data last, or the data that's closest to like your actual test distribution last is a good idea.
Thank you.
Thank you for the very clear presentation. I had a question because you mentioned that the model, when you evaluate on synthetic data, you usually overestimate how well your model is doing. And to me, there is a tension here with what I heard previously when it was said that synthetic data is actually more creative, or can be more creative and more diverse compared to what a human annotator would do. So I would think at that point, if I'm using more creative data, it's probably more likely that I would get a lower benchmark compared to like the average usage. But now you're saying it's actually in the opposite direction. How do you reconcile the two?
Yeah, that's a really good question. And so I have one thought about this, which is that when we're generating synthetic data versus synthetic evaluation data versus training data, the goals are a little different. With training data, as Alisa showed, having low accuracy can kind of be smoothed out by like the properties of machine learning. Whereas when you're doing evaluation, that's not really that acceptable. And so you might need a higher threshold for accuracy for evaluation data, and diversity will necessarily come at that expense.
Thank you.
Yeah, but
yeah, and I think diversity is really interesting. So like synthetic data in some cases can have higher diversity, in some cases can have lower diversity. So people are really bad at enumerating things. We're really, really horrible at like thinking of all the words we know, for instance. And so if I tell you, come up with like an infrequent word with a word that people don't use very much, you're not going to be able to do it. It's like, really, really tough to come up with a lot of them. But on the other hand, the internet is full of infrequent words. So you can, like natural human generated data is going to have more infrequent words if you look at the whole internet. But the data we enumerate from our brains is going to have like a bias distribution towards the top. So it kind of depends on each. And in the evaluation, I think we're suffering from the fact that the evaluation data kind of comes from a natural distribution, whereas the like language model generated comes from a like, less natural distribution than that.
Hi, thank you so much for the tutorial. I'd love to pick the brains on all your team on something you sort of glossed over. I haven't seen it like very analyzed in depth, but it was the point that you made on how LLMs as critics always tend to overestimate the performance, right? And this nags at me for a while because we train these models to make people happy, and people like to be right, right? So I've been wondering if there's something wrong at the basis of how we started training these, and if this objective, this task, goes directly against what they're meant to be good at. And do you think like there's a way to flip that around, or should we like it's cheap to keep doing it, but do you think it will eventually be better and we will eventually just train like a different race, so to speak, of models that are actually good at telling people they're wrong?
yeah, if I just to make sure I understand, is the idea that because language models are trained firstly to imitate human preferences, but then human utterances, but then second, they're like SFT'd or RL trained to make people happy in a sense. Therefore, like it's more likely to make someone happy by giving a response of 5 rather than a 1. And so therefore, these critics might be biased to give a high score based on how they're trained. Is that the question?
Yeah.
Yeah.
I'll just say first, I love the way you stated that. That was that was wonderful. But yeah, I think actually Prometheus, the one that he cited here, was a language model that was specifically trained to be good as a judge. And I think we'll need to do that in order to come up with models that can be accurate critics. And if you do that, then I think you can more or less overcome the model's biases to being biased towards giving positive examples. But if you just use something like GPT-4, no matter how good a model it is, it's going to be a little bit biased. they're also very biased by the in-context examples that you provide to them. So if you say, here are some examples, this one's 50, this one's 75, and this one's 100, it'll be like super biased to giving an answer of 50, 75, or 100. So yeah.
I think one other idea here would be to actually use a smaller model for your critic that might help you avoid inheriting too many biases. And there's a paper recently from it's called Weaver, I think by John Saad Falcon, that was on that topic. And I think it's using smaller critics, there's a lot of promise there.
Great, thank you.
And I think now we'll turn it over to Xiang, who is on Zoom.
Hey, Vijay, can you hear me?
Yes.
Okay, cool. Hi, everyone. My name is Xiang Yue, and I'm postdoc at SMU, and I'll just cover the scenario-specific applications. And sorry for not being in person due to visa issue. So how can we use the synthetic data? So we'll mostly cover the applications of in different kinds of scenarios. And specifically, we will cover 4 scenarios in this tutorial. The first one is reasoning, where, very recently people are very, very interested in like, how can we train better reasoning models for solving complex problems? And the second scenario we'll talk about is the code generation. And then we'll talk about the tool usage and the agent scenarios. And finally, we'll cover the multilingual and multimodal synthetic data generation. So firstly, about reasoning. So people right now are quite interested in, training those kind of reasoning LLMs for solving complex reasoning problems. For example, like OpenAI got this kind of O1 or O3, O4 series. And DeepSeek also released the R1 models. And those kind of reasoning models are recently achieved very impressive performance, say, on IMO, like Olympic level mathematical problems. So for training those kind of reasoning models or for improving the reasoning performance, one of the very important techniques here is so-called the chain of thought, where basically, instead of letting the model directly generating the answers, we just let the model first generate the rationales for solving the problems and then followed by the answers. And more recently, people find that it's also very effective to scaling up the inference compute, where basically we mean that we generate longer chain of thoughts. For example, previously, maybe we just spent like 200 tokens in answering these kind of questions. But right now, we try to let the model to generate longer sequences where, for example, we generate 2,000 tokens for solving more complex or reasoning problems. And the question here is, how can we generate the synthetic reasoning data? Because, for those kind of reasoning scenarios, often like generating reasoning traces by humans is very costly. So the key here is, can we leverage the synthetic data generation techniques we talked about in the previous part for the reasoning specific scenarios? I think one of the most popular approaches is just still like do the sampling based generations, where basically maybe we collect a bunch of queries and then let the LLMs to generate the responses. So for example, we got this kind of query set, and then we sample a bunch of queries from the query set, and then we send it into the teacher model and let the teacher model to generate this kind of chain of thoughts completions. And then we kind of get the final answers. And in some cases, if we know the ground truth answers of this kind of queries, and we can just compare the answers generated models with our ground truth. And those use the so-called reject sampling, where basically if the generated answers does not match the ground truth answer, and we discard this kind of responses. And one of the efforts in this space is called the mass instruct of the mammals, where basically we first collect a bunch of mathematical queries from different kinds of sources. And then we use the models, for example, like Llama or the GPT-4, to basically generate the answers. And after generating answers, like we said, we just compare the generated answers with the ground truth answer annotated by the humans. And we also have like two types of answers or thoughts. One called the chain of thought, which is basically the language of thought, and the other one is called the program thought, where we basically just let the model to generate the pattern programs to solve mathematical problems. And from the result, we can see that firstly, the synthetic data improve the reasoning performance. As for example, we can compare with the base model after we adding the synthetic data, synthetic reasoning traces into the fine-tuning process, we can boost the reasoning performance a lot. And secondly, we can also compare the hybrid results, which is the red bar, and with the yellow and the green ones. And we can see that the hybrid results improve the reasoning performance. Since the math instruct is mostly using the GPT-4 to generate the synthetic reasoning traces, and after that, open math instruct say, okay, maybe we can use some open weights model like Mistra model to synthesize solution as well. In that fashion, maybe we can reduce the cost and avoid some proprietary issues. And so the authors use Mistra model, which is a MOE model, to synthesize solutions for the GSM-AK and math questions. And they propose a metric so-called the TSC, or training set coverage, which basically measures how many training problems are solved correctly by any of the generated answers, where basically, for each of the queries, the authors just try to generate a bunch of the solutions for each problem. So as long as, one of the solutions just get it right, and it can, get 1 point in this kind of TSC metric. So as we can see that with more solution sample, the data could cover more training queries. And finally, the author just generate like 1.8 million solutions in total and use it to fine-tune reasoning models. So we mostly talk about we can just prompt the language model to generate solutions, but meanwhile, we can also prompt the language model to generate the question as well. So for example, in MetaMath, where basically the authors just prompt a GPT 3.5 model to do the question bootstrapping. For example, we can basically feed the existing queries and then let the language model to paraphrase the question. And we can also generate some other types of questions like self-verification question, forward question. For example, where basically we can mask one of the key variables in the question and then ask the model, say, what is the answer, what is the value of this kind of unknown variable? And in that fashion, we can do different kinds of bootstrapping format of this original question. And definitely the author also do the answer augmentation, which is kind of similar to the techniques we just covered in the math instruct and open math instruct. And open math instruct 2 kind of combine the techniques of question bootstrapping as well as answer augmentation, where basically they generate both they augment both solutions and questions, and they use Llama 3.1 405B instruct to generate math data, and they generate 15 million data in total, and then they just fine-tune a Llama 3.1 AB instruct model, and you could see that with more SFT data, synthetic data added into the training, we can see the reasoning performance get improved, especially on those kind of harder reasoning questions when you compare with the base model you're going to fine-tune. And one of the very interesting takeaways from their paper is basically they found that the models actually remain pretty robust, even if in some cases there are some low quality synthetic data added into the training, because this is something unavoidable when we generate the synthetic data. Even though in some cases we can do the filtering, but still in many cases, we can have low quality SFD data or SFD synthetic data. But in this paper, the authors found that actually in some cases, especially in this kind of reasoning scenarios, the models are actually pretty robust. So for example, you can see even if there are like 20% of the data or even 40% of the low quality data added into the training, the model could still achieve relatively high performance when compared with 100% of the high quality data. But however, if you like add more incorrect data or more noisy data, for example, like 80%, definitely you can see the performance drop a lot. But still, we can see some great hope that even if in some cases we have some low quality data when doing the fine tuning, the model could still tolerate this kind of noise. And more recently, like there's a paper called the Open Source, where basically their goal is try to train open source reasoning models based on the existing open source queries. So basically, they develop a rigorous data curation pipeline where they first collect a bunch of questions and then do the filtering and duplication. And then they do kind of like a mixing from like different kind of question sources. And finally, they generate like multiple responses for those kind of questions using a larger reasoning models, say the QWQ32B. And in that fashion, they generate like more than 1 million reasoning traces in total. And the authors just trained the reasoning models on this kind of 1 million thoughts. And then they found that, okay, the reasoning performance on math coding and maybe science reasoning can be boosted a lot. And we can also see the clear scaling effect here, which basically means that if we can have more reasoning data added into training, we can usually gain better performance. And actually, another way for training this kind of reasoning models or generating reasoning data is actually we do not necessarily need to leverage another model to generate the reasoning data, but instead we can just like train this kind of model from scratch or just from a base model using RL. We are basically, for example, like DeepSeek R1 trained this kind of reasoning model from the DeepSeek base model, and they found that okay, as long as we have a like the correct reward here, we can just train the model using the RL, let the model to generate the synthetic solutions, and then use a rule-based reward to see whether the generated solution is correct or not. If it's correct, we just assign them a positive signal, and if it's wrong, we just send them a negative signal. And in that fashion, the author just found that, okay, we can let the model generate the solutions themselves. And actually, we can see the clearly like the length scaling effect, where the model learn to generate longer and longer reasoning traces. And this is so-called like there is so-called aha moment, where basically during this kind of RL training process and in some certain step, the model just miraculously know to do the reflection. And that's the so-called aha moment. Okay, so we basically talk about like how we can generate the synthetic data for the reasoning scenarios. And then we move to the code generation, which is also another very important application scenario for using the synthetic data. So to enable the model to generate the code given a natural language instruction, so we actually need to generate like, for example, like the instruction program pairs. And there are a bunch of solutions for solving that. But typically, we can either prompt the language model to generate this kind of code instruction data based on some C data. It's kind of like in a self-instruction manner. Or we can just prompt the language model to generate the instruction data from the source code, which is a very widely used approach. Because for source code, we have lot of such kind of data available, for example, on GitHub, right? But then we just do not know like what is the purpose of having such M code. So we just prompt a language model to generate the instruction for this kind of source code. So that is kind of like widely used approach right now. Since for the code, we can actually, after we generate the code, we can just execute code and then get the feedback from for example, the interpreter, right? So a natural question here is, can those kind of models understand the execution feedback from the interpreter? And in our previous paper, we found that only the models that were trained on those kind of feedback data could understand this kind of execution feedback. So, for example, like the wither coder, which are basically just trained on the code instruction pairs, they do not have the ability to understand the execution feedback. So the question is, how can we let the model to understand the code feedback? So we, and in the open code interpreter paper, we come up with 5 methods to generate the synthetic data so that we can teach the model to understand the feedback data. So firstly, we can just pack the single turn into the multiple format. And also we can simulate the real user interaction. And thirdly, we can collect some wrong code generation and then try to prompt the language model to crack the previous wrong solutions. And then we can also collect some leak code problems. And in the leak code problems, we already have similar problems and also the follow-up questions. And in that fashion, we can create those kind of synthetic data so that we can teach the model to understand the code feedback data. And actually, using those kind of data, we can just train this kind of code model that we have this kind of code instruction. We can have this kind of natural language instruction, and then we write the code. And after that, we can execute the code and get the feedback. And if there's something wrong, and the model just knows to revise the previous solutions. And from the results, we can see that with the execution feedback, we can get improvement compared with a single turn, and also with human feedback, we can get the performance further improved, and with Oracle feedback, we can get the most capable performance. So that means the more accurate the feedback, the greater the improvement the coding model can achieve. Okay. And then we move to the tool use and agent setting, because one of the very important aspects for using language model is that we really hope they can use external tools to augment their capabilities. And one of the early efforts is called the tool former. Where basically they hope that the language model themselves can teach. The language model can teach themselves to use tools. And in this paper, they basically invested like 4 kinds of tools, like QA tool, calculator, MT is machine translation, and there's also another one we call the Wikipedia search. And basically, the author just try to prompt the language model themselves to generate those kind of such kind of tool usage data, and then fine tune themselves on this kind of generate data to teach themselves to use tools. So for example, in the right of the figure, you can see that we can just have this kind of few shot prompting, where basically we give some examples of this kind of tool usage, and then we prompt the language model themselves to generate such kind of data. And after that, we can just fine tune the model on those kind of generated data. And then there's a kind of follow-up work called the gorilla, where basically, instead of letting the model to generate those kind of data from scratch, the authors cracked more APIs call here. So they basically collect 1,600 API calls in total, and 94 from Porsche Hub, and 600 from TensorFlow, and 900 from Hugging Face. So in those kind of API hubs, we have like different kinds of API calls for different kinds of usage, and then they can have like similar formats. And then they use a self-instruct method, which we covered in the previous part, and also together with some in-count examples to generate the instruction API pairs. So they totally generate like 16 instruction API pairs and use it to fine-tune a model, so-called Gorilla model. And they also try two kinds of settings. So one is a kind of zero shot setting, where basically just have the instruction here, and then they basically just solely rely on the Gorilla model to kind of like give an API call. And they also have that kind of retrieval setting where basically in many cases we have the document for this kind of API, right? So they can just have this kind of document together retrieved with the instruction and feed into the model, so that the model can better understand the instruction, the context together with the API document, so that they can have a better call for the kind of APIs. And after that, after they got the correct API calling, they can execute the API and get the results. So that's basically the Gorilla. And similarly, there's concurrent work called the GPT-4 tools, but they mostly tackle the multimodal setting. So for example, in some cases, we can have an image, and we also have some image content, for example, like the image title or the image description. And the idea here is like we can prompt a language model like ChatGPT with image title, content, and definition of the tools. For example, there are different kinds of tools like image detection, image generation, OCR, captioning, pose detection tools here. And then we can just prompt the language model to see what kind of tools they need to call to finish this kind of instruction. And they also include training cases that when to use tools and when not to use tools. And in that fashion, we can teach the model whether the model actually need a tool for this kind of query. And further, there's a paper called 2LM, where basically further scale up the API or tool usage to, for example, like 16,000 APIs from the rapid API basis. So the basically here is that when we scale up the API calls, then it will pose great challenge for the model for like when to call these kind of APIs, right? And also like how can we have those kind of diverse instructions for those kind of APIs, right? So the overall data generation idea is kind of similar to the previous work we talked about. We are basically just prompt ChatGPT to generate instruction for this kind of APIs. But in this paper, one difference here is that in many real world scenarios, the instruction is a little bit complex. So in those kind of complex scenarios, in many cases, we just need to call multiple APIs instead of only one single API or one single tool. So when generating data, we actually need to prompt the model to generate like multi-tool usage data. So that's the difference that covered in this paper. And also another novelty in this paper is that when generating the response, they kind of like prompt a relatively advanced strategy to search for a valid solution path. Because if they got like different kinds of API calls or API usage for a single instruction, maybe that's a path or solution searching is a little bit complexing. So the author proposed a more advanced search strategy in this kind of cases to enable more accurate solution generation. Okay, and since we also can use tools for the reasoning scenarios as well. So for example, in Torah paper, they basically claim that okay, if we have this kind of reasoning problem, definitely we can have this kind of rationale based or natural language based solution, and we also can have this kind of program based solutions. But how about we just compare like the natural language plus with the Python tools, and basically maybe we can first think about like how can we solve this problem, and then we generate the solutions, right? So in that fashion, they got like this kind of two integrated reasoning. Then like the question is like, how can we generate such kind of data for these kind of reasoning problems? So they first do the so-called imitation learning, where basically just prompt a large model or teacher model to generate such kind of data in those kind of formats. And then they can got the kind of valid trajectories. For example, they can just do the reject sampling, right? And then they can train or fine-tune a smaller language model on those kind of valid trajectories and got this kind of fine-tune model M. And then they can further augment the models using this kind of fine-tune model M with the existing problem. So basically, they can feed the problem again into this fine-tune model, and then they can collect the valid trajectories, as well as they can collect the invalid trajectory, maybe the trajectory leading to the wrong answers. And then they can prompt the teacher model again to correct this kind of wrong trajectories. And in that fashion, they can augment more solutions in an iterative fashion and further fine-tune the previous model checkpoint. Okay, and then we move to the agent scenario, which is kind of similar to the tool usage scenario as well. Because in the agent scenario, we also involve like different kinds of tool usage. And one of the data generation papers or working in this kind of agent scenario is called agent tuning. We are basically just collect like bunch of agent data, for example, like this kind of operating system, web navigation, and web shopping. So they can collect those kind of trajectory as well as the queries as well as the trajectories. And basically, they can like generate the instruction for this kind of scenarios. And then because they can have some filtering, where basically maybe some trajectory lead to the wrong action and some trajectory lead to the correct action. And then they can just keep only the trajectory which leads to the high reward or correct action. And then they can fine tune a model that can basically finish this kind of agent tasks. And then they could just test the models on some held out tasks. So in that fashion, we can teach the model generate correct actions for different kinds of agent scenarios. And there's also another paper which is called the Code Act or Code Act Instruct, where basically the high level idea is like instead of using other format of action, we can just use executable Python code as the actions, and in that fashion we can unify all of the agent actions into a single space, right? Just the coding or the Python executable Python code space. For example, in this kind of case, the user asks the question like find the sum of the reciprocal of the roots of a formula, and basically, we can just generate the Python code for solving this kind of problems, and then maybe we can get some feedback from the kind of the Python executor, which is kind of similar to the open code interpreter work we talked about. And in that fashion, we can generate the code act instruct data and maybe potentially fine-tune a smaller model in the future. And also we can have the computer use scenarios where basically, we want to teach the model to use computer to help us finish the task. And here the authors just employ like two procedures to generate the syntax data. So firstly, it's about the thought completion. We are basically, in many trajectories, we only have the next action, but we do not have like why we want to like execute this kind of action. So the author first prompt the language model to kind of like, generate the missing solution for this kind of action. And then they got this kind of trajectory boost where basically, maybe in the original trajectory, they only have this kind of single action decision. But, we can prompt a language model to generate like diverse action. And in that fashion, we can have more diverse trajectories to fine tune the model. Okay, so this is, and finally, we just covered the multilingual and the multimodal part. So firstly, since we talk about the multilingual and the back translation, as we also covered in previous part, is a very important data generation method. And in this paper, for example, NLRB, which is a very powerful open source machine translation system, done by Meta. And one of the important data generation methods is a back translation. However, they also found that when we add more and more data from mining or back translation, we are basically they start to see the diminishing improvements. That's also a kind of an issue we are facing when using the synthetic data. And when talking about the multimodal scenarios, there's a very well-known works called Lava, which basically they just try to generate the visual instruction tuning data by only using the text-only language models. So for example, given an image, we can have the captions, and we can also have some annotated bounding boxes by humans. And in that fashion, we can just feed this kind of captions as well as the box information into a text language model like a GPT-4, GPT-4 text-only version. And then we can generate like different kinds of instruct and response pairs. And in this paper, the author just generated like 3 different kinds of responses, like the conversation, detailed description, as well as the complex reasoning. And we just first collect some manual examples as seed examples, and then prompt GPT-4 text versions to generate such kind of examples. And by training on such kind of examples, we can see that even a smaller model can have the ability to generate very long and detailed responses for a given image. And when combining the multilingual and the multimodal scenario together, we can also generate synthetic data for this kind of scenario. So in our previous work, which is called Pangea, we generate like 6 million synthetic data instructions in 39 languages. So basically, there are different kinds of solutions or data generation methods we can employ. Definitely, we can do the translation. But in some cases, translation does not solve the cultural issues where, some images are just very cultural specific images. So in that paper, we try to generate more cultural diverse images. We first filter the cultural images from the Lion multi data sets using a text language model based on their alt text. And then we try to do the recaptioning for this kind of image, because we previously got this kind of relatively short caption associated with image, but we can prompt the language model to generate longer captions for this. And after that, we can generate the instruction responsive pairs for this kind of image. And then we can fine tune the model on this kind of multilingual and multimodal instruction data. And from the results, we can see that our model's performance is quite impressive when compared with the OpenWith model on both English and multilingual performance. Okay, so I think that's all for this part, and I'm happy to take any questions.
We're also a little bit over time, so maybe we can have Xiang go next, then
Okay.
So we'll have time for questions.
Um, the slides are not. Oh. Oh. Can you directly jump to the open questions part? Slide 189. Okay, yes. Okay, and thanks, Xiang, for presenting the last section. I'm Yizhong. I recently graduated from the University of Washington, and I'm going to join UT Austin as an assistant professor next year. So let's move on to this section, this last section of this tutorial, limitations and the open questions. Before diving into this, let me give you a quick summary of what we have discovered so far. In the first section, Graham introduced the motivation. Why do we need synthetic data? And what is a high quality synthetic data? Then in the second section, Alisa talked about how can we get the data. She basically summarized the existing methods into 5 categories and also introduced the techniques for data filtering. Then in the third section, Vijay talked about how do we use the synthetic data in different stages of model training, from pre-training to supervised fine-tuning to reinforced learning and to evaluation. Then in the fourth section, Xiang just now detailed the 4 popular application domains where synthetic data is heavily used. These includes reasoning, code generation, tool use, and agents, multilingual and multimodal scenarios. So in this final section, let me talk about the limitation and open questions regarding synthetic data. I have picked up 3 topics that I think are the most important as of now. These are not about the specific techniques or the specific scenarios, but regarding the general concept of synthetic data, the role of synthetic data, and the issues the community is seeing now. First, I would like to review the gap between synthetic data and real-world data. So in contrary to synthetic data, real-world data refers to the data that are produced by real users as they interact with the service or the product in a natural setting. I also want to note that human data may not mean real-world data. Today, as AI services are becoming deeply integrated into our daily lives, the size of real-world user interactions is also increasing fast. ChatGPT has revealed this information that they have 1 billion user messages every day by the end of last year. And Google has also reported processing about 480 trillion tokens each month by mid this year. In comparison, the synthetic data sets that people currently generated are much smaller. Therefore, it cannot really capture the really match the real-world data in terms of diversity and richfulness. This will make the model trained on only synthetic data heavily rely on its generalization capability to perform new user requests. In most cases, this is also auto-distribution generalization, which may not be very robust and satisfying. If we think further, the ways that these 2 types of data that are produced are fundamentally different. The design of synthetic data sets is usually dictated by the developers using language models, while real-world data sets are generated by global population. Therefore, we want to remind the community that despite of all the fast progress of synthetic data, our community also should be paying more attention to the real world usage of our models. A good example was this CLIO paper published by Anthropic last year. They provided an in-depth analysis of the direct traffic on their cloud AI service, which was the first public report on a major AI assistant. But unfortunately, they focused mostly on the top use cases, which people might be very familiar with, not the long tail and novel behaviors of their models. Alternatively, there are some public data sets like WellChat and LM6Chat 1 million for getting insights of the real world usage of our models. And there are some open source tools like a tree that we introduced very recently for conducting the analysis. But here we also want to call for more data releases and studies to understand the long tail usage and the emerging demands in the real world. Another important perspective for comparison is the data quality. One work last year started this in an image classification setup, and they found that synthetic data still underperforming real data in training image classifiers. Their analysis also showed the reason is because that synthetic data still often contain generator artifacts. In this example from the paper, you can find the eyes. You can find the eyes and the mouth of the generated tabby cat are still quite weird. And sometimes there might be some distort class relevant visual content in the above example. You can see that the generated image of this Airbus A320 has 2 engines, while in reality it should only have 1. This reveals the imperfections of synthetic data, and some of these might be quite subtle that are very difficult to detect, but it actually affects the model training negatively. Unfortunately, I think the current synthetic data community haven't placed enough emphasis on the data quality control. Many synthetic data sets these days do not have the quality checks. They just release the data, and this irresponsible behavior actually make the resulting data sets less convincing and risky to be adopted. In most practices, people mainly have 2 assumptions of the data quality. The first assumption is that if the model being trained gets better downstream performance, we simply believe that the training data has better quality. Secondly, if the data is still, some people believe that if the data is still distilled from or generated from a stronger base model, and the data might be of better quality. A recent study showed that both of them are not always true. There are many moving factors, and often you need a good match among these different factors to get the optimal performance. These questions, what should be good indicators of data quality? I believe that the community should be working on methods that can measure the quality at the instance level. There are some existing methods as introduced by our early presenters, including using reward models, using language models as judges, using rule-based verification, and task decomposition. But all of them so far only work for specific types of data. In general, I think how to build a generalist verifier still remains a very hard open problem. Okay, next, I want to dive into the second challenge, the scaling of synthetic data. Today, we are seeing an inevitable trend that more and more model-generated content will appear in model training. This is not only because the model builders want to add them, but also because model-generated content model-generated content might populate on the internet and get included in your training data unintentionally. A publication on Nature last year revealed this trend that synthetic data sets are growing much faster than the other data sources in post-training language models. So we want to ask, what are the possible outcomes of this scaling of synthetic data? One negative possibility is that the model might collapse. As also explained by Vijay in the third section, some people believe that AI models might risk collapsing when trained on recursively generated data. And they have provided the theoretical proof from the perspective of information. However, on the positive side, in practices, we also have seen that many studies show the model can self-instruct, self-improve, self-refine, self-reward, etc. In other words, an extreme case of synthetic data is that the model can self-improve as well. So what actually makes the difference between the model collapse and the model self-improving? Here, I want to give you some intuitive explanation that bringing the additional information might be the key. Additional information include human selection, editing, and supervision after the model generates the data. It can also include human prior in designing the data generation pipeline, like we did in self-instruct. It may also include the grounded documents, retrieved information, and tool use results, like our early presenters have shown in transforming existing data. And lastly, I also want to draw the connection between synthetic data and reinforcement learning, because in reinforcement learning, you can build that as model generates the data and get external rewards from interacting with the environment immediately. So an open question also arises here that whether we can synthesize new information that is useful. I personally believe that it's possible by mimicking our human behavior to generate new information. And this will lead to new knowledge discovery in data synthesis. Okay, finally, I want to discuss the licensing situation of synthetic data. An essential step when you have built a good data set and want to release it is to decide a proper license. But I want to explain why this is tricky in the current situation. Let's take this ultra feedback dataset, for example. Ultra feedback is a very high quality, readily used synthetic preference dataset. This is its Hugging Face page. You can see here that the author generously released this dataset with MIT license, although they have spent tons of money on building this dataset using some API services. This MIT license basically allows other people to use, modify, and redistribute this dataset freely. But we also noticed that this dataset is actually sourced from multiple original datasets. They may have different licenses. Some of them are less permissive or have unclear licenses. This is the first concern, that MIT license might be not proper here. In addition, Ultra Feedback actually used the 17 models in generating all the responses in this dataset. We noticed that not all these models are distillation friendly. What do I mean by distillation friendly? We can take a look at the terms of services from some representative models. First, let's take a look at DeepSeek. It clearly states that using the outputs of their services for training other models is allowed, which is very nice and good news for distillation, our synthetic data community. On the contrary, OpenAI, Anthropic, and Gemini all state that you cannot use their services to develop models that compete with them. However, they didn't clearly define what competing means. With this being said, an open question is how they can inform this restriction. it's not only because the copyright of AI-generated content is unclear, but also because detecting the use of model outputs in training another model is technically very hard. All these concerns leave the practices of synthetic data right now quite chaotic and at the risks of the practitioners and developers. So we call for the community to think about how to address this for a sustainable future of synthetic data and data-centric AI overall. All right, I have finished the three problems, and let me quickly summarize the open challenges and our proposals. First, we compare synthetic data versus real-world data in terms of diversity and quality. In terms of diversity, we propose that the community needs to understand the richfulness of real-world data and try to close the gap. In terms of quality, we believe that we should develop better quality checks and verification methods so that we can promote high-quality data. We then discussed the scaling of synthetic data, and I argue that bringing in the additional information is the key for model self-improving and how to avoid the model collapse. For licensing and copyright, we call for the community. We call for lawful guidance on the use of synthetic data and the community for technical innovation and ethical practice when using synthetic data sets. All right, I have finished the last part, and this is the end of our tutorial, and we are open to questions.
So we have about 10 minutes for questions. We'd be happy to discuss.
Yes.
Hey, I wasn't able to attend the very beginning, so I'm sorry if this came up in the first half. But one thing I didn't see for creating more diverse data was using personas with different personalities, different preferences, which may become more important with educational applications or agentic things where you're trying to help people solve tasks where their preferences really matter. Do you have anything to comment on that generally or specifically?
Yeah, there is a good paper that used persona to generate, I think, 1 million messages, like something like that at that scale. And we actually have a paper called Tulu that used that technique to diversify our synthetic data sets generation. Yeah, it was very effective.
It's not in your slide.
Yeah, sorry, we didn't include it. So.
Yeah, I have one additional comment about this, though, which is language models tend to be very stereotypical if you ask them to do a particular persona. So just to give an example, if you ask it to generate, like, you're somebody from Texas, people from Texas are pretty typical of people from the US. I mean, they're like a little bit off, but a little bit off from like the average US persona, right? But if you ask it to generate something from Texas, it'll come up with things like, I've got a snake in my boot, or, like these things that are like very, very different than what a normal, Texan would say. So I think this is actually an open question, how you can create things that are based on a persona, but also very representative of what that persona is actually like, as opposed to being, very stereotypical.
Maybe we can take one from over there.
Thank you very much for the fantastic tutorial. I have one question about the test data leakage. Do you know whether there are studies whether the data generator having been exposed to the test data from downstream performance has impacts on the students' downstream task performance? Did I make sense?
The question is about the data leakage in generating synthetic data for training, but the generation might be based on some test sets or like some information of the test sets.
So basically, what happens if the data generator has access to the test data?
Oh, I mean, it definitely helps in terms of the final downstream performance. And I think some people might be already doing that. Like, I don't think they are like doing, they are directly like using the test examples to do the generation, but they might have some information like the domains or like the problem styles of the test set, and like people use synthetic data to improve their performance.
Yeah, I actually think this is a really important problem, and it's also really hard to solve because the standard tools people use to generate data even in the academic literature is using proprietary models, and we don't know what data is in those models. And so it's impossible to certify that you're not contaminated if you're using GPT-4 as your generator. So one solution to that is to use the very few models with open data like Almo, but you can count those on one hand, how many of those there are. So it's a huge problem, and I don't know if there's a clear solution to there.
You can actually try to fine tune the open weight models with the test data to different extent, and you can actually see like whether there is a correlation between how much it's been exposed to the performance of the student model.
Well, with the open data models, you can definitely check the contamination. With open weights models, you can estimate it, but even then it's not so obvious how to do that.
You can like the researcher can fine tune them with the test data before generating the data for the students.
Correction. Yeah, so like controlling data, right? Whether it affects like contamination now.
Thank you.
Hi again. So maybe this is a step aside from the main topic of the tutorial, but here the main aspect was to follow natural language, but we see many models that talk to each other, like agents talking, or you can have models talking to infrastructures like managing networks, and so we even see, I think it was DeepSeek in the thinking traces, which do not really follow. Sometimes it's a bit of linguistic garbage, but still in the end, the answer is correct. So there is one aspect of generated data that you did not mention is AI interactions, which can lead to non-natural language. So have you seen things about that? Do you think there are issues? This is a promising direction for some aspects, or what are the dangers, like AI talking a new language that we would not understand? But you see my point. It's yeah.
Oh, I don't have anything super clever to say. I know that there was this paper that was, it was like an image generation, right? And they were saying that these like image generators will develop a secret language or something like that. But I don't remember exactly the context. As far as I thought that was debunked. I'm not sure like if you have AI communicate with AI over a long period of time, and it maybe train on those conversations, whether it would actually develop a secret language. I don't know, but go for it.
So I think it depends what your goals are. Like, if your goals are to have human interpretable traces, then obviously that's a problem. And I think like in most cases, we're looking for systems that interact with humans in some way. So if we have like a reasoning model, there was just recently the OpenAI examples of solving the IMO, International Mathematical Olympiad problems. And they trained a model with lots and lots of reinforcement learning and no enforcement that the explanations still sounded natural. And if you actually read the explanations, they're very weird. Like, they don't sound like natural English. But they still won the IMO gold medal. So I think they achieved their goal of winning an IMO gold medal, but before they could actually like ship it to humans, they'd need to enforce naturalness constraints. But I think it's not that hard to enforce naturalness constraints. You can, include some fine tuning data that still maintains the language to be natural. If I'm worried about like AI talking with AI and humans not being able to understand that, there's there's much easier ways to do that. Like, for example, they can encrypt their communication or something like this. So I'm not I'm not super worried about that evolving naturally because there's much easier ways to do that than it evolving naturally. But yeah, that's just my opinion.
Okay, thank you. I know it was a bit open, but thank you.
Hello. I have a question about is it possible to use synthetic data to improve common sense understanding for large language models? So because I see sometimes large language models still struggling to answer some common sense questions. Some kind of common sense knowledge is too common, but nobody to speak it clearly. So in Chinese, there is a data set called 弱智 bar, maybe low intelligence bar. There's some very, very simple question. Nobody say that. But I don't know if it's possible to use some synthetic data to improve common sense knowledge understanding.
I think, okay, yeah, my advisor works a lot on common sense, so I think I'm being summoned to answer this question. I think it's difficult for exactly the same reason that you're stating, right? Like models aren't good at answering these questions, and so that also makes it difficult to explicitly state what the common sense knowledge is. I think the theme in this tutorial has been like, if you're clever about it, maybe you use some existing knowledge bases which exist, those common sense knowledge graphs. Maybe you can elicit that information better, or you involve human annotators to write some things out explicitly that maybe like there's a missing link in the model logic or something like that. I can see it being helpful for sure, but I kind of think that models will always have these kinds of surprising gaps in terms of like, you think that they're really like winning IMO gold medals, but there are, right, like problems that are common sense, but they can't answer. That might just always, it might be difficult to overcome. I think we don't really train models the way that like humans are learn naturally.
Okay, thank you.
Thanks for the great tutorial, guys. I have a question which kind of builds off the previous question, which is a lot of the synthetic data preparation pipelines and analysis and usages model building, which you guys talked about, was more in domains which were verifiable or had some sort of epistemic certainty. I'm just wondering if there's a sense of, like, for example, even in scenario specific applications, one of them was like reasoning, but there are certain domains in reasoning, like maybe philosophy or healthcare or something, which are not, which don't have as much certainty or rule-based verifiers. I'm wondering if you guys have a sense of how synthetic data generation can work for these kind of scenarios.
I think the question is how synthetic data can be used in like not easily verifiable domains. I think in some sense it's already like the origin of like using like language model generated synthetic data was for open-ended questions or open-ended instructions. So in that case, it's not like verifiable, but most of the people just distill from like better language models and it can work. So the verification is for like how to validate the quality of the data. I think like if we currently for some verified domains, we can verify the quality of the data, but for open-ended like domains, it's very hard. And there are some solutions, but I don't think they are perfect right now. Like using reward models or LM judges, right? Yeah.
Right. Yeah. I think the question was more of the whole like paradigm of like self-improvement base is dependent upon the
Oh, the
clean reward,
self-improving.
clean reward function. So I'm guessing, is there like certain directions where this can be extended to the relatively unverifiable or uncertain domains?
I think there are two. I'm aware of two directions. One is how to build reward models or like some sort of verification system for the like kind of open-ended domains. Another direction is like how training on verifiable domains can generalize to unverifiable domains and started this kind of like generalization. I'm not sure if that.
One other comment is back translation or instruction back translation can be very helpful here. So like if you want to teach a model to write good philosophy essays given a prompt, you can take a good philosophy essay and generate the prompt. Because generating the prompt is a lot easier than generating a good philosophy essay from a model that hasn't been trained on good philosophy essays.
Right, yeah.
And so I think that as long as you're starting with good seed data, it doesn't necessarily need to be on verifiable domains to get synthetic data to work well. So that would be my first step there. Further steps, lots of creativity for future work, I guess.
Right, okay. Thanks.
And we're almost out of time, so let's just take 2 more questions.
Okay, so in the last part, you mentioned that it is assumed that a bigger and a more advanced model can generate better synthetic data, but you said that's not true. Could you elaborate more about this?
Yeah, there is a recent paper from Graham's group led by Kim et al. And they show that so because I think the conclusion is the reason is the stronger model might be skewed towards the specific distribution in the data generated. So it probably lacks the diversity, and that diversity is useful for the target evaluations. So there are like a different entanglement between these different factors. So empirically, the strongest model they used, I think the cloud, like Cloud Sonnet or something, is not the best performant model for generated the target data. Yeah.
Okay, thank you.
So thanks for the tutorial. I have a question. You mentioned distillation restrictive models. Is there a known way to detect if a model was distilled using some other model?
Yeah, the question was, is there a way to detect if a model was distilled from another model? I know there's the we can answer that in the front if you want to come up here. Sorry about that. And thank you all for attending this tutorial.
You're. Yeah. Fine. I think they would, or at least they have slaves. Oh, you had your, yeah. There's a website as well.